Hello, and welcome back to the Sleepy Professor, where knowledge flows as gently as a meandering river through a moonlit valley. This is your sanctuary from the day's urgencies, a place where curiosity meets tranquility, and where the most profound mysteries of our universe unfold at the perfect pace for drifting minds. Tonight, we embark on a journey that spans billions of years, traveling deep into geological time to explore one of Earth's most paradoxical forces. Volcanoes, these mountains of fire and stone, these restless sculptors of our world, have accidentally and quite beautifully built the very foundation of everything we hold dear. Before we begin this gentle exploration, I invite you to settle deeper into your comfort, perhaps adjusting your pillow or pulling a blanket a little closer. I'm always quietly delighted to imagine these words floating across oceans and continents, finding their way to curious minds in cozy bedrooms from Auckland to Alaska, from Stockholm to Singapore. If these sleepy scientific wanderings bring you peace, a gentle like-il subscription would mean the world to me, and to those already part of this growing constellation of nighttime learners, thank you for making this possible. Now, don't worry, I'll do my best not to make tonight's journey so fascinating that it keeps you awake. But if it does, at least you'll drift off with your mind full of the most extraordinary story ever told, how mountains that breathe fire accidentally created oceans that cradle life, atmospheres that sustain civilizations, and soils that feed the world. There are certainly worse things to dream about than the volcanic forces that transformed a barren rock into our blue marble home. So how exactly did these seemingly destructive forces of fire and molten stone end up gifting us such a gentle, life-sustaining world? The answer, as we'll discover, lies in understanding volcanoes not as occasional violent outbursts, but as patient, tireless architects working on a timescale so vast that human history becomes merely the final sentence in an epic geological novel. When Earth breathed only fire. Imagine, if you will, stepping into a time machine and travelling back 4.5 billion years to witness Earth's violent birth. What you would find is not the serene blue planet of today, but a hellish sphere of molten rock, glowing cherry red against the cosmic darkness. This was Earth's infancy, a time when our world was less a planet than a glowing ember, cooling slowly in the cold vacuum of space. The young Earth was a place where the very concept of solid ground was meaningless. Rivers of lava stretched across continents that didn't yet exist. The atmosphere was thick with steam and toxic gases, and the surface temperature approached that of molten copper. Volcanoes weren't rare visitors to this landscape. They were the landscape itself, erupting from every crack and fissure in the planet's thin, unstable crust. This fiery childhood wasn't an accident or catastrophe. It was a necessary beginning, as essential to Earth's development as a cocoon is to a butterfly. You see, our planet formed through what cosmologists call accretion, countless fragments of rock, ice, and dust, colliding and sticking together in the early solar system. Each impact released tremendous kinetic energy, heating the growing world until it became a ball of magma. Picture it, asteroid-sized chunks of debris, some traveling at tens of thousands of kilometers per hour, smashing into the growing Earth with the force of millions of nuclear weapons. Each collision added mass, but also tremendous heat, gradually melting the planet from the surface inward. Heavy elements like iron and nickel, being denser, sank toward the center, forming Earth's molten core. Lighter materials, silicon, aluminum, oxygen, floated upward, eventually cooling to form the first primitive crust. But this crust was incredibly thin and fragile, like the skin that forms on cooling pudding. The slightest disturbance would crack it open, allowing the molten interior to burst forth in spectacular volcanic displays. These weren't the neat cone-shaped volcanoes we know today, but vast fissures that would stretch for hundreds of kilometers, pouring out oceans of lava that would reshaping entire regions in a matter of days. The Great Outgassing, Earth learns to breathe. During this tumultuous period, something remarkable was happening that would prove essential for life's eventual emergence. Deep within the molten rock were trapped gases, water vapor, carbon dioxide, nitrogen, sulfur compounds, and dozens of other chemical species. Every volcanic eruption was like the Earth exhaling, releasing these gases from the planet's interior into the gradually forming atmosphere. This process, which geologists call outgassing, was Earth's first attempt at creating an atmosphere. With each eruption, each explosive release of pressure, the planet was slowly wrapping itself in a blanket of gases that would eventually make the surface habitable. The water vapor would condense into the first oceans. The carbon dioxide would create a greenhouse effect that kept the planet warm, despite the young sun being about 30% dimmer than it is today. The nitrogen would provide the stable background gas that still makes up 78% of our atmosphere. But this process was far from gentle. The early atmosphere was toxic by our standards. Thick with carbon dioxide, sulfur compounds that would sting the eyes and burn the lungs, and virtually no oxygen. Lightning crackled constantly through the volcanic clouds, creating a perpetual light show against the orange-tinted sky. To us, it would have seemed like a vision of hell, but to a lifeless planet, it was the first step toward paradise. Consider the patience of this process. For hundreds of millions of years, volcanoes erupted continuously, each one adding its contribution to the growing atmosphere and the accumulating pools of water. There was no plan, no intelligence guiding this process, just the inexorable laws of physics and chemistry working on a planetary scale. Heat sought escape, pressure sought release, and in doing so they accidentally created the conditions that would eventually allow life to flourish. When stone flowed like water, during this period, what we now think of as solid rock behaved more like a thick, glowing liquid. Basaltic lava flows would stretch for hundreds of kilometers, creating vast plains of cooling magma. Where these flows met bodies of water, they would create enormous clouds of steam, further thickening the atmosphere with water vapor. The landscape changed constantly. Mountain ranges would rise and collapse within geological moments. Mere thousands of years, entire continents of fresh crust would form, only to be broken apart and remelted as the restless planet continued to churn. It was a world in constant motion, where the only constant was change itself. Yet within this apparent chaos, patterns were beginning to emerge. The heaviest materials continued to sink, the lightest continued to rise, and gradually, very gradually, the planet began to organize itself into the layered structure we know today. A dense iron core, a hot mantle of semi-molten rock, and eventually, a thin but increasingly stable crust. The Moon, formed when a Mars-sized object called Theia collided with the early Earth, played a crucial role in this story. The impact that created our satellite also triggered volcanic activity on a scale that's difficult to comprehend. Oceans of magma covered entire hemispheres of the planet. But the Moon's gravitational pull also began to stabilize Earth's rotation and create tides that would, millions of years later, help shape the coastlines of the first continents. As we settle into this story, imagine the profound silence that must have characterized this period. Not the absence of sound, but its impossibility. Sound requires an atmosphere to travel through, and while Earth was developing its first primitive atmosphere, it was still too thin and too hot to carry sound the way we know it. The most tremendous volcanic explosions would have occurred in an eerie, muffled quiet, their violence expressed only in light, heat, and the slow reshaping of the landscape. This was Earth's age of fire, when our planet learned its most fundamental lesson, how to release the heat and pressure of its violent birth in a controlled way, through the safety valves we call volcanoes. Without this process, Earth might have remained a molten ball indefinitely. With it, the stage was set for everything that would follow: the cooling seas, the thickening atmosphere, and eventually, the first tentative experiments in the chemistry of life. The volcanic gift of oceans. When steam became sea. As you continue to settle into comfortable relaxation, let's follow one of the most beautiful transformations in Earth's history, the birth of the oceans from volcanic breath. For millions of years after the planet's formation, what would become the Pacific, Atlantic, and other great bodies of water existed only as steam and vapor, suspended in the thick, choking atmosphere above a surface too hot for liquid water to survive. Every volcanic eruption during this period was essentially the planet weeping, releasing water that had been locked away in rock and mineral crystals deep in the Earth's interior. This wasn't water as we know it, flowing and blue and life-giving, but superheated steam under tremendous pressure, mixed with sulfur compounds and other gases that would be toxic to life as we know it. Picture the Earth during this time as a vast sauna, where water existed everywhere but could never condense. The atmospheric pressure was enormous, perhaps 10 times greater than today, and the temperature at the surface averaged around 500 degrees Celsius, hot enough to melt lead. Steam swirled in perpetual planet-wide storms, occasionally condensing in the upper atmosphere only to rain back down and immediately vaporize upon contact with the scorching surface. The Great Cooling and the first rains. Gradually, over tens of millions of years, the Earth began to cool. The constant bombardment of asteroids and comets slowed, reducing the input of impact energy. The planet's interior, while still molten, began to stabilize, and volcanic activity, though still intense, became less chaotic. The atmosphere, thick with water vapor, began to act like a blanket, trapping heat but also gradually radiating it away to space. Then came one of the most dramatic events in Earth's history, the first rainfall, when the surface temperature finally dropped below 100 degrees Celsius. Water vapor began to condense not just temporarily, but permanently. The first raindrops to fall on the cooling basaltic plains would have hissed and steamed, but they didn't immediately evaporate. More followed, and more, until what began as occasional drizzle became a planetary deluge that may have lasted for millions of years. Imagine rain falling continuously for geological ages, not the gentle showers we're familiar with, but torrential downpours that would have filled entire ocean basins in mere thousands of years. This was the Earth learning to cry tears of joy after its fiery birth, each drop a gift from the volcanic forges deep below. The chemistry of life's cradle. These first oceans were nothing like the clear blue waters we know today. They were dark, mineral-rich broths, more like a planetary soup kitchen than the pristine seas we might imagine. Every volcanic eruption had contributed not just water, but also dissolved minerals, metals, and chemical compounds that would prove essential for life's eventual emergence. Iron from volcanic springs turned the water rust-colored in many places. Sulfur compounds gave it a sharp, almost medicinal smell. Dissolved salts from countless eruptions began the process that would eventually make seawater the complex chemical solution it is today. A solution so perfectly balanced that it can sustain everything from microscopic plankton to blue whales. The early oceans were also surprisingly warm, heated from below by the still active volcanic systems and from above by the thick greenhouse atmosphere. In many places, the water would have been nearly at boiling point, creating vast regions of hot springs and hydrothermal activity that extended across entire ocean basins. But within this apparently hostile environment, something remarkable was happening. The constant circulation of warm, mineral-rich water was creating chemical gradients and energy sources that would eventually nurture the first living systems. The oceans weren't just a byproduct of volcanic activity, they were becoming a planetary laboratory for the chemistry of life. The volcanic thermostat. As the oceans deepened and spread, they began to play a crucial role in regulating Earth's temperature. The process was elegantly simple. Atmospheric carbon dioxide would dissolve into seawater, where it would react with dissolved minerals to form carbonate compounds. These would eventually precipitate out as limestone and other rocks, effectively removing greenhouse gases from the atmosphere. This carbon cycle, driven by volcanic outgassing and oceanic absorption, created a kind of planetary thermostat. When volcanic activity increased, more CO2 entered the atmosphere, warming the planet and increasing evaporation and rainfall. The increased rainfall would weather more rocks, releasing more minerals into the oceans, which would absorb more CO2. When volcanic activity decreased, the reverse would happen. Earth was learning to regulate its own temperature through a complex dance between fire, water, and atmosphere. This regulatory system was crucial for maintaining conditions suitable for life. Without it, Earth might have experienced runaway greenhouse heating like Venus, or runaway glaciation like Mars. Instead, the volcanic-oceanic partnership maintained a delicate balance that kept liquid water stable on the surface for billions of years. Tides of time. The oceans also began to shape the planet in return. As they deepened, they became massive reservoirs of thermal energy, absorbing heat during the day and releasing it at night, moderating temperature swings. The moon's gravitational pull created the first tides, and these rhythmic risings and fallings of the sea level began the long process of coastal erosion and sediment transport that would eventually help build continents. Underwater, volcanic activity continued but took on new characteristics. Submarine volcanoes created pillow lavas, strange bulbous formations that occur when molten rock encounters cold seawater. These underwater eruptions built seamounts, ridges, and eventually islands, adding complexity to the ocean floor and creating the first diverse underwater landscapes. The hydrothermal vents that formed around these submarine volcanoes became oases of chemical activity. Superheated water, rich in minerals and dissolved gases, would shoot up from the seafloor like underwater geysers. Around these vents, chemical reactions occurred that would later provide energy sources for the first living organisms. As we continue our gentle journey through deep time, it's worth pausing to appreciate the profound beauty of this transformation. The same forces that had made early Earth seem like hell were now creating the blue world that would become life's cradle. Fire had given birth to water, destruction had enabled creation, and the planet was learning to nurture rather than simply endure. The oceans that cover more than 70% of Earth's surface today are the direct descendants of that ancient volcanic breath. Every wave that laps against a shore, every raindrop that falls, every glass of water we drink carries within it the memory of that first great transformation when steam became sea and a violent world began its journey toward becoming a gentle one, breathing life into the skies. The atmosphere's volcanic birth. As your breathing deepens and your mind settles into the rhythm of this ancient story, let's turn our attention skyward to explore how volcanoes built the very air we breathe. The atmosphere that now sustains all terrestrial life, from the oxygen in your lungs to the nitrogen that makes up most of each breath, has its origins in the fiery exhalations of Earth's restless interior. In the beginning, Earth had no atmosphere at all. The newly formed planet was too small and too hot to retain the light gases that might have surrounded it during its formation. Any primordial atmosphere would have been stripped away by the solar wind, that constant stream of charged particles flowing from our young, active sun. So the air we breathe today isn't a leftover from Earth's birth, but rather a careful construction project that took billions of years to complete. Every volcanic eruption was like the planet taking a breath, or more accurately, learning how to breathe. With each explosion, each gentle outgassing from hydrothermal vents, each fissure eruption, gases that had been locked away in rock and magma were released into the growing atmosphere. Carbon dioxide, water vapor, nitrogen, sulfur compounds, hydrogen, methane, a complex cocktail of gases that would have been deadly to us, but was essential for preparing Earth for life. The Great Atmospheric Experiment. The early atmosphere was a masterpiece of accidental chemistry. Picture it, thick clouds of steam and volcanic gases swirling around the planet, lit from within by constant lightning and from below by the glow of lava flows. The air pressure was crushing, perhaps 10 times what it is today, and the composition was utterly alien. Carbon dioxide made up as much as 80% of the atmosphere, with nitrogen beginning its slow accumulation toward the 78% it comprises today. But within this seemingly toxic environment, fascinating chemical reactions were taking place. Lightning crackling through volcanic clouds was creating complex organic molecules. Amino acids, the building blocks of proteins, formed spontaneously in the electrified atmosphere. Ultraviolet radiation from the young sun, unfiltered by any ozone layer, was breaking apart simple molecules and recombining them into more complex forms. The atmosphere wasn't just a protective blanket, it was a vast laboratory where the chemistry of life was being explored for the first time. Methane, belched out by volcanic vents, created a powerful greenhouse effect that helped keep the planet warm, despite the young sun being significantly dimmer than today. This faint young sun paradox puzzled scientists for decades. How could early Earth have remained warm enough for liquid water when the sun was putting out 25% less energy? The answer lay in the volcanic atmosphere, which trapped heat so efficiently that Earth remained comfortably warm even under the weaker solar radiation. Nitrogen, the quiet foundation. While carbon dioxide and water vapor get most of the attention in discussions of early atmospheres, nitrogen played an equally crucial role. This seemingly inert gas, which makes up more than 3/4 of the air we breathe today, was slowly accumulating through volcanic outgassing. Unlike other atmospheric components, nitrogen is remarkably stable. It doesn't react readily with rocks or dissolve easily in water, so once it enters the atmosphere, it tends to stay there. This stability made nitrogen the perfect foundation gas for a planetary atmosphere. While carbon dioxide levels fluctuated with volcanic activity and ocean absorption, while water vapor condensed and evaporated with temperature changes, nitrogen provided a steady background that helped stabilize atmospheric pressure and density. It was like the bass note in a complex musical composition, not flashy but essential for the harmony of the whole system. Over millions of years, as lightning and ultraviolet radiation worked on the nitrogen-rich atmosphere, some of it was converted into more reactive compounds like ammonia and nitrates. These nitrogen compounds would eventually become essential nutrients for life, but in the early atmosphere, they added another layer of chemical complexity to an already rich mix. The carbon dioxide thermostat. Carbon dioxide, perhaps more than any other volcanic gas, shaped the early climate of Earth. Unlike today, when we worry about too much CO2 in the atmosphere, the early Earth needed high carbon dioxide levels to stay warm. The process was elegantly self-regulating. When volcanic activity increased, more CO2 was released, warming the planet. This warming increased evaporation and rainfall, which weathered more rocks, releasing minerals that would eventually absorb CO2 from the atmosphere and lock it away in carbonate rocks. This carbon cycle created a kind of planetary thermostat that has kept Earth's climate relatively stable for billions of years. When the planet gets too hot, increased weathering removes more CO2, cooling it down. When it gets too cold, volcanic activity continues to add CO2, warming it up. It's a feedback system so elegant that it seems designed, yet it emerged naturally from the interaction of volcanic gases, water, and rock. The carbon dioxide also played a crucial role in the eventual emergence of life. When dissolved in water, it forms carbonic acid, which helped weather rocks and release nutrients into the early oceans. It also provided the carbon atoms that would become essential building blocks for all organic molecules. Every carbon atom in your body, in your DNA, your proteins, your cellular membranes, can trace its lineage back to CO2 that once billowed from ancient volcanic vents. Sulfur, the unexpected catalyst. Among the most pungent and seemingly hostile of volcanic gases was sulfur dioxide, which gave the early atmosphere its sharp, acrid smell. Yet sulfur compounds played surprisingly important roles in preparing Earth for life. They formed aerosols in the upper atmosphere that helped regulate temperature by reflecting sunlight. They participated in complex atmospheric chemistry that created organic sulfur compounds essential for life, and they provided energy sources that the first living organisms would learn to exploit. Even today, some of the most ancient metabolic pathways in living cells involve sulfur chemistry, suggesting that life's earliest experiments in extracting energy from the environment made use of the sulfur-rich conditions of the early Earth. Bacteria living around modern volcanic vents still use sulfur compounds as an energy source, just as their ancestors might have done billions of years ago. The patient architecture of air. What's most remarkable about the volcanic construction of Earth's atmosphere is its patience. This wasn't a quick process. It took hundreds of millions of years for the atmosphere to reach the composition and pressure that could support complex life. Volcanic eruptions occurred sporadically, sometimes separated by thousands of years, yet each one added its contribution to the growing atmospheric reservoir. The atmosphere also had to learn to protect itself. Ultraviolet radiation from the sun was gradually breaking apart water molecules in the upper atmosphere, allowing hydrogen to escape to space while leaving oxygen behind. This slow accumulation of oxygen, combined with volcanic outgassing, gradually built up the chemical diversity that would eventually support photosynthesis and complex life. As you breathe in and out, following the gentle rhythm of sleep, remember that each breath connects you to this ancient story. The nitrogen filling your lungs was exhaled by volcanoes billions of years ago. The trace amounts of argon and other noble gases are volcanic gifts that have circulated through the atmosphere for eons. Even the oxygen, though added later by photosynthetic life, depends on the volcanic foundation that made that life possible in the first place. The atmosphere surrounding us isn't just air, it's a library of Earth's history, a protective blanket woven from volcanic breath over geological time. Every sunset colored by atmospheric particles, every breeze carrying the sense of life, every breath that sustains consciousness, all are reminders of the day when volcanoes first taught the Earth how to breathe. The chemistry of Genesis, volcanic laboratories of life. As we drift deeper into this story of planetary transformation, let's explore one of the most profound mysteries in science. How did lifeless rock and gas give rise to living, breathing, thinking organisms? The answer, increasingly, points to volcanoes as nature's first and most prolific chemistry laboratories, places where the random mixing of elements accidentally stumbled upon the recipes for life itself. Imagine the early Earth not as a single uniform environment, but as a vast collection of natural laboratories, each with its own unique conditions. Volcanic hot springs bubbling with mineral-rich water, deep-sea hydrothermal vents shooting superheated, chemically complex fluids into the cold ocean depths, shallow volcanic pools that would dry out and refill with each tide, concentrating dissolved compounds, lightning-charged volcanic clouds where electrical energy drove chemical reactions impossible under calmer conditions. Each of these environments was conducting its own chemical experiments, mixing and remixing the basic elements of life in countless combinations. Carbon from volcanic CO2, nitrogen from volcanic gases, phosphorus from weathered volcanic minerals, sulfur from hydrothermal vents. All the essential elements were there, along with energy sources to drive reactions and concentration mechanisms to bring reactive molecules into close contact. The sulfur paradox. One of the most fascinating aspects of early biochemistry involves sulfur, an element that seems hostile to life. Think of the choking smell of volcanic gases, yet appears to be essential for life's origins. Modern research has revealed that many of the most ancient metabolic pathways in living cells are based on sulfur chemistry. The iron-sulfur clusters found in enzymes throughout the tree of life bear a striking resemblance to minerals that form naturally around hydrothermal vents. This suggests that life's earliest experiments in metabolism may have taken place in environments saturated with volcanic sulfur compounds. Rather than being poisonous, these sulfur-rich conditions provided both the chemical building blocks and the energy sources that primitive organisms needed to get started. Even today, some of Earth's most ancient bacterial lineages derive their energy not from sunlight or organic matter, but from sulfur compounds of the type that volcanoes have been producing for billions of years. The beauty of this system lies in its self-organization. Volcanic activity creates chemical gradients, sharp differences in temperature, pH, and mineral content over short distances. These gradients naturally concentrate certain compounds and separate others, creating the kind of organized chemical environment that complex molecules need to form and persist. It's as if volcanoes were unconsciously solving one of the hardest problems in the origin of life: how to create order from chaos. Carbon, the master builder. Carbon dioxide pouring from volcanic vents provided the raw material for all organic chemistry, but getting it to form complex molecules required special conditions. Volcanoes provided these in abundance: high temperatures and pressures that could force molecules together, metal catalysts in the form of volcanic minerals, and cycling conditions that could concentrate and purify reaction products. In shallow volcanic pools, for instance, cycles of heating and cooling, drying and flooding would have created natural distillation systems. Simple organic molecules formed during one cycle could be concentrated and further modified during the next. Over thousands or millions of cycles, this process could potentially build up the complex organic polymers, proteins, nucleic acids, lipids that life requires. Some of the most intriguing research in this field focuses on hydrothermal vents, where alkaline fluids from the Earth's interior meet the slightly acidic waters of the early oceans. This creates natural electrochemical cells, living batteries that could drive the formation of organic molecules. The mineral structures that precipitate around these vents have microscopic pores and channels that could have served as primitive cell membranes, concentrating organic molecules and protecting them from the harsh external environment. The iron connection. Iron, one of the most abundant elements in volcanic emissions, may have played a crucial role as life's first catalyst. Iron-sulfur minerals forming around hydrothermal vents can catalyze many of the chemical reactions that living cells use to build complex molecules from simple starting materials. In essence, volcanic minerals were doing biochemistry before biology existed. This connection between iron and life runs deep. Even today, iron sits at the heart of hemoglobin, the molecule that carries oxygen in our blood. Iron-sulfur clusters are essential components of the electron transport chains that power cellular respiration. Many scientists believe that these biological uses of iron are evolutionary echoes of chemistry that first took place in volcanic environments billions of years ago. The abundance of iron in volcanic systems also helped solve another crucial problem for early life: protection from harmful radiation. Iron minerals can absorb and deflect ultraviolet radiation, creating protected microenvironments where delicate organic molecules could persist. This natural sunscreen effect may have been essential for allowing complex chemistry to develop on a planet bathed in harsh radiation from the young sun. Phosphorus, the energy currency. One of the most challenging elements for early life to acquire was phosphorus, which is essential for DNA, RNA, and ATP, the molecules that store and transfer both genetic information and energy in living cells. Phosphorus doesn't form many soluble compounds under normal Earth surface conditions, making it difficult for primitive organisms to obtain. But volcanoes changed this equation dramatically. Volcanic activity can create unusual phosphorus-bearing minerals that dissolve more readily than typical phosphate rocks. Meteorites heated by impact-generated volcanism can also deliver phosphorus in more accessible forms. Some researchers have even suggested that volcanic lightning could have created soluble phosphorus compounds from atmospheric gases. The result was that volcanic environments were among the few places on early Earth where all the essential elements for life, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and trace metals were present in forms that could participate in complex chemistry. It wasn't just that volcanoes provided these elements, they provided them in the right combinations, concentrations, and chemical forms to make life possible. Trace elements, the hidden helpers. Beyond the major elements, life requires dozens of trace elements, metals like zinc, copper, molybdenum, and manganese, that serve as cofactors in enzymes and other biological molecules. The modern biosphere obtains these elements primarily through the weathering of rocks and the circulation of ocean water, but on the early Earth these processes were much less efficient. Volcanic hydrothermal systems, however, are extraordinarily effective at extracting and concentrating trace elements from rocks. The superheated water that circulates through volcanic systems can dissolve metals that remain locked away under normal conditions, then deposit them in concentrated form when the water cools or changes pH. This natural metallurgy created environments where trace elements essential for life were available in much higher concentrations than elsewhere on the planet. Even more intriguingly, the specific suite of trace elements found in hydrothermal systems closely matches the elements that life uses most extensively. This could be a coincidence, but many scientists suspect it reflects life's origins in volcanic environments. We use these particular elements because they were the ones most readily available to our earliest ancestors. The gentle violence of creation. As your mind drifts between waking and sleeping, carried along by this story of chemical genesis, consider the beautiful paradox at its heart. The same volcanic forces that could destroy complex molecules with their heat and caustic gases were also the forces that created those molecules in the first place. Life didn't emerge despite volcanic activity, it emerged because of it. This pattern of creative destruction runs throughout Earth's history. Volcanoes provided the chemical raw materials for life, then continued to challenge life with their eruptions, forcing evolution to explore new possibilities. They created the first complex organic molecules, then later threatened those molecules with their emissions, driving the development of protective mechanisms and metabolic flexibility. The chemistry of life, it seems, was forged in fire, not the gentle, controlled fire of a laboratory burner, but the wild, unpredictable fire of volcanic vents and pools. Every enzyme in your body, every strand of DNA, every molecule that makes consciousness possible, can trace its ancestry back to those first chaotic experiments in volcanic chemistry. And remarkably, this process continues today. In the deep ocean around hydrothermal vents, the same chemistry that gave rise to life billions of years ago is still operating. Minerals are still catalyzing organic reactions, gradients are still driving molecular assembly, and the boundary between geology and biology remains beautifully blurred. The volcanoes that built our world are still building it, still experimenting, still exploring the infinite possibilities hidden in the marriage of fire and water, rock and life. Deep ocean forges. The hidden architecture of life. As we descend now into the deepest parts of our story, quite literally into the depths of the ocean where sunlight has never penetrated, we discover some of the most remarkable volcanic features on Earth. These are the mid-ocean ridges and hydrothermal vents, hidden kingdoms of fire and water that may represent nothing less than the birthplace of life itself. Imagine drifting downward through kilometers of dark water, past the last traces of sunlight, past the familiar world of fish and whales, into the abyssal depths where the pressure would crush any surface dweller instantly. Here, in this alien environment, towering chimneys rise from the seafloor like underwater skyscrapers, belching clouds of superheated, mineral-rich water into the frigid depths. These are the black smokers and white smokers, hydrothermal vents that represent some of the most extreme and yet most life-rich environments on our planet. What makes these vents so extraordinary is that they exist at the intersection of two seemingly incompatible worlds: the cold, high-pressure environment of the deep ocean and the hot, chemically active world of volcanic systems. Where these worlds meet, magic happens, not the supernatural kind, but the deeper magic of chemistry and physics, creating conditions found nowhere else on Earth. The volcanic heart of the seafloor. The energy that drives these deep-sea oases comes from the same source that has shaped our planet since its birth: volcanic heat from the Earth's interior. Along the mid-ocean ridges, vast underwater mountain ranges that encircle the globe like the seams on a baseball, new oceanic crust is constantly being formed as molten rock wells up from the mantle below. But this isn't the explosive, mountain-building volcanism we're familiar with on land. Instead, it's a gentler, more continuous process. Imagine molten rock oozing out of cracks in the seafloor like honey from a broken jar, cooling instantly upon contact with seawater to form strange pillow-shaped formations. These pillow lavas accumulate layer upon layer, building the foundation of new ocean floor at a rate of just a few centimeters per year. Yet even this seemingly gentle process generates tremendous heat, and where seawater manages to penetrate down through cracks in the newly formed crust, it encounters temperatures hot enough to melt copper. The water doesn't boil because of the immense pressure at these depths, but it becomes superheated, reaching temperatures of 400 degrees Celsius or more while remaining liquid. As it circulates through the hot rocks, it becomes a powerful solvent, dissolving metals and minerals that would remain locked away under normal conditions. Chemical gardens in the abyss. When this mineral-rich, superheated water finally bursts back out of the seafloor, it creates one of the most spectacular sights in the natural world. The sudden temperature contrast between the hot vent water and the near-freezing ocean causes dissolved minerals to precipitate out almost instantly, forming towering chimneys that can grow meters in height within years. These chimneys are natural skyscrapers built from the inside out, as mineral-rich water continues to flow through their cores, depositing new layers with each circulation. The chemistry happening at these vents is incredibly complex. Iron sulfides create the black smoke of black smokers, while sulfates and carbonates create the white plumes of white smokers. Copper, zinc, lead, gold, and dozens of other metals precipitate out in fantastic formations. Some vents create fields of metallic icicles hanging from the seafloor. Others build elaborate terraces and pools that look like mineral versions of Yellowstone's hot springs. But what's most remarkable about these chemical gardens isn't their beauty, it's their biology. Despite the crushing pressure, the toxic metal concentrations, and the extreme temperatures, these vents support some of the most vibrant ecosystems on Earth. Giant tube worms, some as thick as human arms and meters long, sway in the mineral-rich currents. Ghostly white crabs scuttle across mats of bacterial films. Schools of pale fish patrol the borders between the hot vent water and the cold ocean depths. Life without light. These vent ecosystems exist in complete darkness, yet they thrive with an abundance that rivals tropical rainforests. The secret is chemosynthesis, the process by which bacteria and archaea harvest energy not from sunlight, but from the chemical reactions between vent fluids and seawater. These microscopic organisms form the foundation of food webs that exist entirely independently of photosynthesis, proving that life can flourish even in the absence of solar energy. The bacteria at these vents use sulfur compounds, methane, hydrogen, and other chemicals as energy sources, converting them into organic matter through metabolic pathways that may be among the most ancient on Earth. These chemosynthetic organisms have learned to extract energy from the same chemical reactions that power the volcanic systems themselves, creating a beautiful symbiosis between geology and biology. Many scientists now believe that these deep-sea vents may represent the closest thing we have to Earth's original nurseries of life. The combination of chemical energy, mineral surfaces that could catalyze reactions, and the natural compartmentalization provided by porous mineral structures creates ideal conditions for the complex chemistry that life requires. Here, in the deepest, darkest places on our planet, we may be witnessing processes that are essentially unchanged from those that gave rise to the first living cells billions of years ago. The mineral scaffolds of existence. The mineral structures that form around hydrothermal vents aren't just beautiful, they may have been essential for life's origins. The precipitating metals create microscopic pores, channels, and chambers that could have served as natural test tubes, concentrating organic molecules and protecting them from the harsh conditions of the early ocean. Iron-sulfur minerals, which form abundantly at these vents, can catalyze many of the chemical reactions that living cells use to build complex molecules from simple starting materials. Even more intriguingly, these mineral structures can maintain steep chemical gradients, sharp differences in pH, temperature, and chemical composition over very short distances. Such gradients are essential for driving the chemical reactions that life depends on, yet they're difficult to maintain in open water where everything quickly mixes and equilibrates. The complex architecture of vent deposits creates thousands of tiny microenvironments, each with its own unique chemistry, each potentially experimenting with different approaches to the challenge of organizing matter into living systems. Modern molecular biology has revealed striking similarities between the chemistry of life and the chemistry of hydrothermal vents. The iron-sulfur clusters that sit at the heart of many essential enzymes are nearly identical to minerals that form naturally around vents. The metabolic pathways that some of Earth's most ancient bacteria use to extract energy from chemical reactions closely mirror the inorganic chemistry occurring in vent systems. It's as if life learned its basic tricks by apprenticing itself to volcanic chemistry. Gardens of metal and steam. As you drift deeper into relaxation, imagine floating through these underwater landscapes where biology and geology merge into something entirely unique. Gardens of metallic chimneys rise like alien forests, their surfaces encrusted with bacterial mats that shimmer with colors not found anywhere else on Earth. Deep purples and oranges and golds, created by microorganisms that have evolved to thrive in conditions that would instantly kill most surface life. The giant tube worms that cluster around active vents have no mouths, no stomachs, no way of eating in any conventional sense. Instead, their bodies are filled with symbiotic bacteria that harvest chemical energy from vent fluids and share the organic compounds they produce with their hosts. It's a partnership between animal and microbe that may echo the very earliest collaborations between different forms of life. Strange crabs with eyes that have evolved to detect the faint glow of hot vent water scuttle across fields of bacterial mats. Fish with antifreeze proteins in their blood patrol the boundaries between scalding vent water and frigid ocean depths. These creatures represent evolution's most creative solutions to the challenge of living at the intersection of fire and ice, chemistry and biology. The planetary circulation system. These deep ocean volcanic systems do more than support exotic life. They're also crucial components of Earth's planetary circulation systems. The mid-ocean ridges, stretching for more than 60,000 kilometers around the globe, represent the largest mountain range on Earth. Though hidden beneath kilometers of water, they're constantly producing new oceanic crust at a rate that completely replaces the ocean floor every 200 million years or so. This process, called seafloor spreading, is part of the grand tectonic dance that shapes our planet's surface. As new crust forms at mid-ocean ridges, older crust is pushed away, eventually diving back into the mantle at subduction zones where it melts and begins the cycle anew. The continents themselves are passengers on this slow-moving conveyor belt, drifting across the planet's surface at rates of a few centimeters per year. The hydrothermal circulation associated with this process moves enormous volumes of seawater through the oceanic crust, altering its chemistry and temperature. The minerals and gases released by hydrothermal vents influence ocean chemistry on a global scale, affecting everything from the pH of seawater to the availability of nutrients that support marine life throughout the world's oceans. Ancient echoes in modern cells. Perhaps most remarkably, the influence of these deep ocean volcanic systems extends far beyond their immediate environments. Every living cell on Earth, from bacteria to blue whales to human beings, carries within its biochemistry the molecular echoes of hydrothermal vent chemistry, the metabolic pathways that power cellular respiration, the enzyme systems that facilitate protein synthesis, even the basic mechanisms by which cells extract energy from their environment, all bear striking similarities to the inorganic chemistry occurring at volcanic vents. This suggests that life didn't simply emerge at hydrothermal vents and then move on to other environments. Instead, life may have been so thoroughly shaped by its volcanic origins that it carries those origins with it everywhere it goes. We are, in a very real sense, walking extensions of the same chemical processes that occur at the bottom of the ocean, around volcanic vents that most of us will never see. As the gentle rhythm of sleep begins to take hold, let yourself imagine the vast networks of volcanic activity hidden beneath the world's oceans. Miles below the surface, in crushing darkness and under unimaginable pressure, volcanic forges continue their ancient work. They're building new crust, cycling elements between Earth's interior and its surface, and maintaining the chemical gradients that may have given rise to life itself. These hidden volcanic systems are reminders that our planet is not a finished work, but a dynamic living system that continues to create and recreate itself. The same processes that built the first continents and filled the first oceans are still operating today, still experimenting with new combinations of chemistry and physics, still exploring the boundaries between the living and non-living worlds. In the deepest places on Earth, where fire meets water and chemistry becomes biology, the story of our planet continues to unfold. And in the quiet darkness of the ocean depths, volcanoes continue their patient work of building worlds, not just shaping the physical landscape, but nurturing the chemical processes that make life, consciousness, and dreams themselves possible. Architects of continents. The slow construction of solid ground, as your breathing deepens and your consciousness begins its gentle drift towards sleep. Let's turn our attention to one of the most patient and persistent construction projects in the history of our planet, the volcanic building of continents. Over billions of years, through countless eruptions and countless cooling cycles, volcanoes have quite literally built the ground beneath our feet, raising solid land from the primordial oceans and creating the stable platforms upon which all terrestrial life depends. When Earth was young, most of its surface was covered by deep oceans. The early crust was thin, dense, and unstable, more like the oceanic crust we find at the bottom of today's seas than the thick, stable continental crust that now supports our cities and forests. The emergence of true continents required a slow process of volcanic accumulation, where lighter, more silica-rich rocks gradually built up into masses too buoyant to be subducted back into the mantle. This process began at volcanic island arcs, chains of volcanoes that formed where oceanic plates collided and one dove beneath another. Each eruption added a little more material to these growing accumulations of land, and over millions of years what began as scattered volcanic islands gradually coalesced into the first small continents. These early land masses were nothing like the continents we know today. They were smaller, more fragmented, and constantly being reshaped by continuing volcanic activity. Islands born of fire. The birth of volcanic islands offers us a window into how this continental construction process works. Consider the Hawaiian island chain, where a deep mantle plume has been punching through the Pacific plate for millions of years, creating a trail of volcanic islands that stretches for thousands of kilometers. The Big Island, still volcanically active, represents the current position of the hotspot, while the older islands to the northwest show various stages of volcanic evolution and erosion. Each Hawaiian island began as a submarine volcano, erupting on the deep ocean floor and slowly building upward through miles of water until it finally broke the surface. The moment when a new volcanic island first emerges from the ocean is one of the most dramatic events in geology. Imagine a mountain of fire rising from the depths, its summit finally breaking through the waves to create new land where none existed before. But the emergence from the sea is just the beginning. Young volcanic islands are barren places, nothing but cooling lava and volcanic ash, with no soil, no plants, no animals. Yet given time, these sterile landscapes become gardens. Seeds arrive on ocean currents, and in the feathers of migratory birds, spores of ferns and mosses drift on the wind from distant continents. Gradually, life colonizes these new lands, and the volcanic soil, rich in minerals from the fresh lava, proves remarkably fertile. The Galapagos Islands provide perhaps the most famous example of this process of biological colonization. When Charles Darwin visited these relatively young volcanic islands in 1835, he found them populated by unique species that had evolved in isolation. The famous finches, the giant tortoises, the marine iguanas, all descendants of colonists that had somehow crossed hundreds of miles of ocean to reach these volcanic newcomers. The patient building of mountain ranges. On a grander scale, volcanic activity has been responsible for building many of the world's great mountain ranges. The process typically begins at subduction zones, where oceanic plates dive beneath continental margins, generating the magma that feeds chains of volcanoes along the edges of continents. The Andes Mountains of South America, stretching for more than 7,000 kilometers along the western edge of the continent, represent the most spectacular example of this process in action. The Andes weren't built in a day, or even in a millennium. They're the cumulative result of millions of years of volcanic activity, as the Nazca Plate has slowly dove beneath the South American plate, generating magma that has built volcano upon volcano, layer upon layer, until the mountains now reach heights of nearly 7,000 meters above sea level. Many of the peaks are still active volcanoes, reminders that this construction project is far from finished. Similar processes built the Cascade Range of the Pacific Northwest, where the Juan de Fuca Plate subducts beneath North America, creating the volcanic arc that includes Mount Rainier, Mount Hood, and Mount Shasta. The volcanoes of Japan, Indonesia, and the Philippines tell the same story: subduction zones where oceanic crust dives into the mantle, melts, and returns to the surface as volcanic mountain chains. Flood basalts, volcanic megaprojects. Some of the most impressive examples of volcanic continent building involve not individual volcanoes, but vast outpourings of lava that cover enormous areas. These flood basalts represent some of the most massive volcanic events in Earth's history, capable of burying entire regions under hundreds of meters of lava in geologically brief periods. The Columbia River Basalt Group in the Pacific Northwest of North America provides a dramatic example. Between 17 and 6 million years ago, a series of massive fissure eruptions poured out more than 350,000 cubic kilometers of lava, enough to cover the entire state of Washington in a layer more than 100 meters thick. Individual lava flows from these eruptions traveled for hundreds of kilometers, following river valleys and spreading out across vast areas of what are now Washington, Oregon, and Idaho. Even more impressive are the Deccan Traps of India, which erupted around 66 million years ago and may have contributed to the extinction of the dinosaurs. These flood basalts covered more than 1.5 million square kilometers, with lava up to 2 kilometers thick in some places. The scale of these eruptions is difficult to comprehend. They released more lava in a few thousand years than all the world's current volcanoes produce in millions of years. The deep architecture of continents. Beneath the visible landscape of mountains and plains lies the deeper architecture that volcanoes have built over billions of years. Continental crust is fundamentally different from oceanic crust. It's thicker, lighter, and more complex in composition. Much of this complexity comes from the repeated cycles of volcanic activity, weathering, erosion, and remelting that have processed and reprocessed crustal materials over geological time. Deep beneath mountain ranges, vast bodies of granite mark the locations where magma chambers slowly cooled and crystallized. These batholiths can be hundreds of kilometers across and represent the frozen roots of ancient volcanic systems. When later erosion strips away the overlying rocks, these granite cores are exposed as some of the most distinctive landscapes on Earth. Places like Yosemite Valley, carved from the granite remains of volcanic systems that were active more than 100 million years ago. The process of continental building also involves the accretion of exotic terranes, pieces of crust that formed elsewhere and were later added to continental margins by tectonic processes. Many of these terranes are volcanic in origin, representing ancient island arcs or oceanic plateaus that were scraped off subducting plates and welded onto continental edges. The western edge of North America, for example, is a mosaic of such accreted terranes, each with its own volcanic history and each contributing to the complex geology of the region. Volcanic soils, the foundation of life on land. Perhaps the most important contribution volcanoes have made to continental development is the creation of fertile soils. Volcanic rocks weather relatively quickly compared to other rock types, releasing nutrients that plants need to grow. Volcanic ash, in particular, breaks down into some of the most fertile soils on Earth, supporting agriculture and natural ecosystems of extraordinary richness. The relationship between volcanoes and soil fertility helps explain why some of the world's most densely populated regions are found in volcanically active areas. The fertile soils around Mount Vesuvius have supported dense populations for thousands of years, despite the obvious volcanic hazards. The volcanic soils of Java support some of the highest rural population densities on Earth. The volcanic regions of Central America and the Andes have been centers of civilization for millennia. This fertility comes from the chemical composition of volcanic rocks, which tend to be rich in the elements that plants need: potassium, phosphorus, calcium, magnesium, and a host of trace elements. When volcanic rocks weather, these nutrients are released into the soil where plants can access them. Volcanic soils also tend to have excellent physical properties. They're well drained but retain moisture effectively, and their mineral composition gives them the ability to hold on to nutrients rather than allowing them to leach away. The continuing construction project. As you settle more deeply into the peaceful state between waking and sleeping, remember that the volcanic construction of continents is far from finished. New land is still being created in places like Hawaii, Iceland, and the volcanic arcs of the Pacific Rim. The mid-ocean ridges continue to produce new oceanic crust that will eventually become part of continental margins through accretion and collision processes. Mountain ranges continue to rise as subduction zones feed their volcanic chains. This ongoing construction is part of what makes Earth such a dynamic, vibrant planet. Unlike the Moon or Mars, where ancient impact craters remain largely unchanged for billions of years, Earth constantly resurfaces itself through volcanic activity. The oldest oceanic crust is only about 200 million years old, ancient by human standards, but young in geological terms. Even the continents, though more stable, are constantly being modified by volcanic activity, weathering, and tectonic processes. The ground you walk on, the mountains you admire, the fertile soils that grow your food, all are gifts of volcanic activity stretching back billions of years. Every grain of sand on a beach, every pebble in a stream bed, every boulder on a mountainside can ultimately trace its origin back to molten rock that once flowed from the Earth's interior. We live on a planet built by fire, shaped by the patient accumulation of countless volcanic events into the stable, habitable world we call home. And in the quiet darkness of approaching sleep, you can almost sense this deep time at work, the slow but persistent processes that continue to build and reshape our world, the volcanic forces that even now are adding new land to some places while recycling old land in others, all part of the grand ongoing construction project we call Earth. The fertile ashes of renewal, when destruction becomes creation, as consciousness begins to blur at the edges and your body settles into the deep relaxation that precedes sleep. Let's explore one of the most beautiful paradoxes in the natural world: how volcanic destruction becomes the foundation for extraordinary fertility and abundance. This transformation from devastation to verdant life represents one of nature's most profound lessons about the relationship between endings and beginnings, between apparent catastrophe and hidden opportunity. When Mount Vesuvius erupted in 79 CE, burying the cities of Pompeii and Herculaneum under meters of ash and pumice, it seemed like an unmitigated disaster. The volcanic deposits preserved these Roman cities in eerie detail, creating windows into ancient life that have fascinated archaeologists for centuries. Yet within decades of the eruption, the same volcanic slopes that had witnessed such destruction were already showing signs of remarkable recovery. Plants began to colonize the ash-covered landscape, and within a few centuries the region around Vesuvius had become some of the most fertile agricultural land in Italy. This pattern of renewal, following volcanic destruction, has repeated itself countless times throughout Earth's history, in every corner of the world where volcanoes have left their mark. What seems like sterile devastation in the immediate aftermath of an eruption gradually transforms into landscapes of extraordinary biological richness. The secret lies in the composition of volcanic materials themselves. They contain exactly the chemical ingredients that life needs to flourish. The mineral wealth of volcanic soils. Fresh volcanic ash might look lifeless and forbidding, but it's actually a treasure trove of plant nutrients. Unlike the heavily weathered soils found in many parts of the world, where millions of years of rainfall have leached away essential elements, volcanic deposits are rich in minerals that have been locked away in the Earth's interior and are suddenly made available to surface life. Potassium, one of the most important plant nutrients, is abundant in many types of volcanic rock. When these rocks weather, and volcanic materials weather much more quickly than most rock types, they release potassium into the soil where plant roots can absorb it. Phosphorus, another essential nutrient that's often scarce in natural soils, is commonly found in volcanic ash and lava flows. Calcium and magnesium, important for plant structure and photosynthesis, are also abundant in volcanic materials. But it's not just the major nutrients that make volcanic soils so fertile. Trace elements, tiny amounts of metals like iron, zinc, copper, and manganese that plants need for healthy growth are also richly supplied by volcanic deposits. These trace elements often become limiting factors in plant growth on older, more weathered soils, but volcanic areas rarely face such limitations. The physical properties of volcanic soils are equally important. Volcanic ash creates soils with excellent structure. They're porous enough to allow good drainage and root penetration, yet they hold moisture effectively during dry periods. The mineral composition of volcanic soils also gives them a high cation exchange capacity, which means they can hold on to nutrients rather than allowing them to be washed away by rainfall. Ecosystems reborn from fire. The recovery of ecosystems following volcanic eruptions provides some of the most dramatic examples of ecological succession in nature. The process typically begins with hardy pioneer species, plants that can tolerate the harsh conditions of fresh volcanic deposits, and that can establish themselves with minimal soil development. These pioneers are often small, fast-growing plants that can quickly colonize disturbed areas. Lichens are frequently among the first colonizers, forming colorful crusts on volcanic rock surfaces. These remarkable organisms are actually partnerships between fungi and algae or bacteria, and they play a crucial role in the early stages of soil development. The acids they produce help break down volcanic rock, while their organic matter begins to accumulate in cracks and crevices, creating the first pockets of primitive soil. Ferns are also common early colonizers of volcanic landscapes. Their spores can travel long distances on the wind, and many fern species are adapted to grow on bare rock surfaces with minimal soil. As they grow and die, they contribute organic matter that helps build soil and creates conditions suitable for other plants. Gradually, shrubs and eventually trees begin to establish themselves. In tropical volcanic regions, this succession can happen remarkably quickly. Within a few decades, areas that were completely buried under fresh volcanic deposits can be covered by dense forest. The volcanic soils provide such excellent growing conditions that plants grow faster and larger than they might in other environments. Agricultural paradises built on fire. Perhaps nowhere is the fertility of volcanic soils more dramatically demonstrated than in the agricultural regions built around active volcanoes. Despite the obvious risks, some of the world's most productive farmland is found on volcanic slopes, and some of the densely populated regions on Earth are in volcanically active areas. The island of Java in Indonesia provides a striking example. With more than 130 active volcanoes, Java is one of the most volcanically active places on Earth. It's also one of the most densely populated, supporting more than 140 million people on an area roughly the size of England. This population density is possible largely because of the extraordinary fertility of Java's volcanic soils, which support intensive agriculture that can feed enormous numbers of people. The volcanic regions of Central America tell a similar story. Countries like Guatemala, El Salvador, and Costa Rica have built their agricultural economies around crops grown on volcanic soils. Coffee, in particular, thrives in volcanic regions. Many of the world's finest coffee beans are grown on volcanic slopes, where the mineral-rich soils and favorable drainage conditions create ideal growing conditions. Even in temperate regions, volcanic soils support remarkably productive agriculture. The Palos region of eastern Washington and northern Idaho, built on ancient volcanic deposits, produces some of the world's highest wheat yields. The volcanic soils of Oregon's Willamette Valley support everything from grass seed to wine grapes, creating agricultural industries worth billions of dollars. The wine country connection. Some of the world's most celebrated wine regions owe their character to volcanic soils. The mineral composition of volcanic deposits can impart distinctive flavors to grapes, creating wines with unique terroir that reflects their volcanic origins. The stress that vines experience growing on volcanic slopes, combined with the excellent drainage that volcanic soils provide, often produces grapes with concentrated flavors and complex chemical profiles. Sicily's Mount Etna region has become famous for wines that express the character of volcanic terroir. The black volcanic soils on Etna's slopes, rich in minerals and with excellent drainage, produce wines with distinctive mineral notes and exceptional complexity. Similar stories can be told about volcanic wine regions around the world, from the Canary Islands to Chile's volcanic valleys. Forests of fire and renewal. Natural forests growing on volcanic soils often display extraordinary vigor and diversity. The combination of fertile soil and the disturbance regime created by periodic volcanic activity creates conditions that favor high biodiversity. Many volcanic regions support forest ecosystems with unusually high numbers of plant and animal species, often including endemic species found nowhere else. The forests of volcanic regions also tend to be remarkably resilient. Plants growing in these environments have evolved strategies for surviving periodic volcanic disturbances, and many species actually benefit from the mineral inputs that volcanic eruptions provide. Some trees, like certain pine species, have even evolved to take advantage of volcanic fires, with cones that open only under the intense heat of volcanic eruptions, releasing seeds into the mineral-rich ash beds that provide ideal germination conditions. The marine connection. The fertility that volcanoes provide extends beyond terrestrial environments. Volcanic ash that falls into oceans carries nutrients that can stimulate marine productivity. Iron, in particular, is often a limiting nutrient in ocean ecosystems, and volcanic eruptions can provide pulses of iron that trigger massive blooms of phytoplankton, the microscopic plants that form the base of marine food webs. These volcanic contributions to marine fertility can have effects that ripple through entire ocean ecosystems. Increased phytoplankton production supports larger populations of zooplankton, which in turn support larger populations of fish, marine mammals, and seabirds. Some of the world's most productive marine ecosystems are found in regions where volcanic activity regularly enriches ocean waters with nutrients. Cycles of destruction and renewal. As your mind drifts toward the threshold of sleep, consider the profound wisdom embedded in these cycles of volcanic destruction and renewal. What appears catastrophic in the short term often proves beneficial in the long term. The forests that burn in volcanic eruptions are replaced by more vigorous forests growing in enriched soils. The farms that are buried under ash often return as more productive farms as the volcanic deposits weather into fertile soil. This pattern reflects one of the deepest truths about natural systems. They thrive not despite disturbance, but because of it. Periodic disruption prevents ecosystems from becoming stagnant and creates opportunities for innovation and renewal. Volcanoes, with their cycles of destruction and soil enrichment, are among the most important agents of this creative destruction in the natural world. The vegetables in your garden, the coffee in your morning cup, the wine in your evening glass, all may owe their existence to volcanic soils created by ancient eruptions. The forests you walk through, the flowers you admire, the abundance of life you see around you, much of it is built on a foundation of volcanic fertility, on soils created from the ashes of destruction and transformed into the substrates of life. In the gentle transition towards sleep, let yourself appreciate this fundamental truth, that endings and beginnings are not opposites but partners, that destruction and creation dance together in the ongoing symphony of natural renewal. The same forces that can devastate landscapes are also the forces that create the conditions for life to flourish in abundance. Volcanoes, in their patient cycles of eruption and renewal, teach us that from fire can come fertility, from ashes can come abundance, and from apparent destruction can emerge the most beautiful expressions of life's creativity. Evolution's fiery muse. The great evolutionary experiments. As your breathing grows slower and deeper, and the boundary between consciousness and dreams begins to soften, let's explore how volcanoes have served as nature's most persistent and creative force in shaping the course of evolution. Far from being mere obstacles that life has had to overcome, volcanic events have acted as catalysts, accelerators and sculptors of evolutionary change, pushing life to explore new possibilities and adapt to ever-changing conditions. Evolution, we often forget, doesn't occur in a vacuum. It's not a process that unfolds in stable, unchanging environments, but rather one that responds dynamically to environmental challenges and opportunities. And throughout Earth's history, few forces have been more effective at creating both challenges and opportunities than volcanic activity. From mass extinctions that cleared evolutionary playing fields to the creation of new islands, ripe for colonization, volcanoes have been evolution's most influential collaborator. The relationship between volcanoes and evolution begins with a simple but profound truth. Evolution thrives on change. Stable environments tend to produce stable ecosystems, where species become well adapted to existing conditions and evolutionary change slows. But when environments change dramatically, as they do during major volcanic events, natural selection suddenly has new criteria to work with. The species that can adapt to new conditions flourish, while those that cannot face extinction. It's during these periods of environmental upheaval that evolution often makes its most dramatic leaps. Islands as evolutionary laboratories. Perhaps nowhere is the relationship between volcanoes and evolution more clearly demonstrated than on volcanic islands. These isolated patches of land, born from submarine eruptions and initially devoid of life, represent some of the purest evolutionary laboratories on Earth. When plants and animals eventually colonize these islands, arriving by wind, water, or wing from distant continents, they find themselves in environments unlike any they evolved in. The Galapagos Islands provide the most famous example of this phenomenon. When Charles Darwin visited these volcanic islands in 1835, he encountered a living laboratory of evolution in action. The islands, formed by volcanic activity over the past few million years, had been colonized by plants and animals from the South American mainland. But isolation and the unique environmental conditions created by volcanic landscapes had allowed these colonists to evolve in remarkable directions. Darwin's finches, perhaps the most celebrated example of island evolution, demonstrate how volcanic environments can drive evolutionary change. The ancestors of these birds probably arrived as a single species from the mainland, but the diverse ecological niches available on the volcanic islands, from seed-eating opportunities in arid lowlands to insect-catching possibilities in highland forests, allowed them to diversify into more than a dozen distinct species, each with its own specialized beak shape and feeding strategy. The volcanic nature of the islands was crucial to this evolutionary radiation. The varied topography created by volcanic activity, from sea-level lava flows to high-altitude cinder cones, provided a diversity of microclimates and ecological conditions. The different ages of lava flows created a patchwork of habitats, from recently formed bare rock to older flows covered by mature vegetation. This environmental diversity provided the raw material for evolutionary experimentation. The archipelago effect. The Hawaiian Islands tell a similar story of volcanic landscapes driving evolutionary innovation. Over millions of years, as the Pacific Plate moved over a stationary hotspot, a chain of islands was created, each offering slightly different environmental conditions. Species that colonized these islands faced the challenge of adapting not just to one environment, but to a series of related but distinct volcanic landscapes. The Hawaiian Silversword Alliance provides a striking example of adaptive radiation in volcanic environments. Starting from a single ancestral species related to California tarweeds, this plant group has evolved into more than 24 species that occupy habitats ranging from coastal deserts to alpine bogs on high volcanic peaks. Some species grow as low shrubs in dry lava fields, others as sword-like rosettes on cinder slopes, and still others as climbing vines in wet forests. Each has adapted to specific volcanic environments, developing unique strategies for surviving in landscapes shaped by fire. The isolation provided by volcanic islands also allows evolution to explore possibilities that might not be viable on continents, where competition and predation pressure are often more intense. Many island species evolve unusual characteristics: flightless birds, giant insects, dwarf mammals, that reflect adaptation to island conditions where typical evolutionary pressures may be reduced or absent. Mass extinctions and evolutionary renewal. While island evolution provides elegant examples of how volcanic environments can drive speciation, some of the most dramatic interactions between volcanoes and evolution have occurred during mass extinction events. Several times in Earth's history, Massive volcanic eruptions have caused global environmental changes so severe that they triggered the extinction of large percentages of Earth's species. Yet these catastrophic events, devastating as they were, also created opportunities for evolutionary innovation on a global scale. The Permian-Triassic extinction event, which occurred about 252 million years ago, was the most severe extinction in Earth's history, eliminating roughly 90% of marine species and 70% of terrestrial species. This great dying coincided with the eruption of the Siberian Traps, a massive flood basalt province that poured out millions of cubic kilometers of lava over several 100,000 years. The volcanic gases released during these eruptions dramatically altered global climate and ocean chemistry, creating conditions that most existing life forms couldn't survive. But the extinction, catastrophic as it was, also cleared ecological space for new evolutionary experiments. In the aftermath of the Permian-Triassic extinction, new groups of organisms rose to prominence. The archosaurs, ancestors of dinosaurs and crocodiles, began their rise to dominance. New types of marine organisms colonized the emptied seas. The evolutionary story that would lead eventually to mammals, birds, and flowering plants began to unfold in the changed world created by volcanic catastrophe. The Deccan Traps and dinosaur evolution. The End Cretaceous extinction event, which occurred about 66 million years ago and brought the age of dinosaurs to a close, provides another example of how volcanic activity can reshape evolutionary trajectories. While an asteroid impact is often cited as the primary cause of this extinction, massive volcanic eruptions in what is now India, the Deccan Traps, were occurring at the same time and likely contributed to the environmental stress that made recovery from the asteroid impact more difficult. The extinction of non-avian dinosaurs, marine reptiles, and many other groups created ecological opportunities that early mammals were quick to exploit. In the aftermath of the extinction, mammal diversity exploded as these previously small nocturnal creatures adapted to fill the ecological roles left vacant by extinct reptiles. The age of mammals began in landscapes still shaped by the aftermath of volcanic catastrophe. Volcanic highlands and evolutionary isolation. Beyond their role in mass extinctions, volcanoes have shaped evolution by creating geographic barriers and isolated habitats that promote speciation. Mountain ranges, built by volcanic activity, act as barriers to gene flow, allowing populations on different sides to evolve in isolation. The unique environmental conditions found at different elevations on volcanic mountains also create opportunities for ecological specialization. The volcanic mountains of East Africa provide excellent examples of how topographic isolation promotes evolutionary diversification. The highland areas created by volcanic activity in Ethiopia, Kenya, and Tanzania harbor numerous endemic species that evolved in isolation on these sky islands. Many plant and animal species found in East African highlands are more closely related to species in distant mountain ranges than to species in the lowlands just a few kilometers away, reflecting the isolating effect of topographic barriers created by volcanic activity. Climate and evolutionary pressure. Volcanic eruptions have also influenced evolution through their effects on global climate. Large volcanic eruptions can inject sulfur dioxide and ash into the stratosphere, where they reflect sunlight and cause temporary global cooling. These volcanic winters create new selective pressures, favoring organisms that can survive in cooler conditions or that have metabolic flexibility. The Tobus supervolcanic eruption, which occurred about 74,000 years ago in what is now Indonesia, may have created such severe climatic stress that it influenced human evolution. Some researchers suggest that the volcanic winter following this eruption reduced human populations to small groups that were forced to develop new survival strategies, potentially accelerating the development of more sophisticated tool use and social cooperation. Ongoing evolutionary partnerships. As you drift closer to the edge of sleep, Consider that the evolutionary partnership between life and volcanoes continues today. In volcanic regions around the world, plants and animals are still adapting to environments shaped by ongoing volcanic activity. Some species have evolved remarkable tolerance for sulfur compounds, extreme pH levels, or rapid environmental change. Others have learned to take advantage of the disturbance cycles that volcanic activity creates. Many plant species in volcanic regions have evolved strategies for surviving periodic ashfalls or lava flows. Some can sprout from buried root systems after their above-ground portions are destroyed. Others have seeds that remain viable in soil for decades, waiting for the next disturbance event to create favorable germination conditions. These adaptations reflect millions of years of evolutionary partnership with volcanic landscapes. The story of evolution on Earth cannot be told without acknowledging the central role that volcanoes have played as agents of change, challenge, and opportunity. From the smallest island adaptations to the largest mass extinctions, volcanic activity has provided the environmental variation that keeps evolution creative and dynamic. We are not just the products of gradual evolutionary change and stable environments, but the descendants of species that repeatedly faced and overcame the challenges posed by a volcanically active planet. In the quiet moments before sleep, let yourself appreciate this deep relationship between fire and life, between destruction and creation, between the ancient forces that have shaped every living thing on Earth. Evolution and volcanism have been dance partners for billions of years, each influencing the other in an endless choreography of adaptation and change that continues even now, in the gentle darkness as you drift toward dreams of deep time and the patient forces that built our world. When giants awaken, the supereruptions, the sleeping titans beneath our feet. As your consciousness continues its gentle descent toward the realm of dreams, let's venture into one of the most humbling chapters in Earth's volcanic story, the tale of supervolcanoes, those rare but world-changing eruptions that occur perhaps only once every 100,000 years. Yet when they do awaken, they reshape not just landscapes but the entire trajectory of life on our planet. To understand supervolcanoes, we must first abandon our familiar mental image of volcanoes as tall, cone-shaped mountains belching fire and smoke into the sky. Supervolcanoes are different. They're often invisible, hidden beneath seemingly peaceful landscapes of forests, lakes, and rolling hills. They don't build mountains. Instead, they hollow out vast underground chambers filled with molten rock, creating geological time bombs that can slumber for hundreds of thousands of years before unleashing eruptions of almost incomprehensible magnitude. The most famous of these sleeping giants lies beneath the tranquil wilderness of Yellowstone National Park in Wyoming. Visitors come from around the world to marvel at the park's geysers, hot springs, and wildlife, most never realizing they're standing atop one of the most powerful volcanic systems on Earth. The colorful hot springs and reliable eruptions of Old Faithful are gentle reminders of the vast magma chamber that lies several kilometers below the surface, a chamber that has erupted catastrophically 3 times in the past 2 million years. The Yellowstone caldera, a window into geological violence. The last supervolcanic eruption at Yellowstone occurred about 640,000 years ago, creating what geologists call the Lava Creek Tuff. To appreciate the scale of this event, consider that it ejected roughly 1,000 cubic kilometers of volcanic material, enough to bury the entire state of Texas under 0.5 meter of ash. The eruption was so violent that it caused the ground to collapse, creating a caldera, a giant crater that measures about 55 kilometers long and 35 kilometers wide. But even this enormous eruption pales in comparison to Yellowstone's earlier supervolcanic events. The Huckleberry Ridge eruption, which occurred 2.1 million years ago, was more than twice as large, ejecting over 2,500 cubic kilometers of material. To put this in perspective, This single eruption released more volcanic material than all of recorded human history's volcanic eruptions combined, multiplied by 1,000. The ash from these Yellowstone supereruptions traveled incredible distances. Deposits have been found as far east as Iowa and as far south as Texas, blanketing much of the North American continent under layers of volcanic debris. The immediate area around Yellowstone would have been completely sterilized, buried under hundreds of meters of hot ash and pumice. The atmospheric effects would have been global, with volcanic particles and gases altering weather patterns and potentially triggering climate changes that lasted for years or even decades. Toba, the eruption that nearly ended humanity, perhaps even more dramatic in its implications for life on Earth, was the supervolcanic eruption of Mount Toba in Sumatra, Indonesia, approximately 74,000 years ago. This eruption, which created the Lake Toba caldera that visitors can see today, was one of the largest volcanic events of the past 2 million years, ejecting an estimated 2,800 cubic kilometers of material into the atmosphere. The Toba eruption occurred at a critical moment in human evolutionary history. Our species, Homo sapiens, had recently emerged from Africa and was beginning to spread across Asia and into other continents. The timing of the Toba eruption coincides with what geneticists call a population bottleneck in human evolution, a period when our species numbers appear to have dropped dramatically, perhaps to as few as 10,000 individuals worldwide. Some researchers suggest that the Toba eruption created a volcanic winter, a period of global cooling caused by volcanic particles in the atmosphere blocking sunlight. This climatic disruption may have made survival extremely difficult for early human populations, forcing them into small refuge areas where they could find food and shelter. The stress of surviving this volcanic catastrophe may have accelerated certain aspects of human evolution, favoring individuals with greater cognitive flexibility, improved tool-making abilities, and enhanced social cooperation. While the connection between Toba and human evolution remains debated among scientists, the eruption undoubtedly had profound effects on global ecosystems. Ash layers from Toba have been found across South and Southeast Asia, and the climatic effects would have disrupted plant and animal communities across much of the tropics. The recovery from such an event would have taken decades or even centuries, fundamentally altering the evolutionary trajectories of countless species. The patterns of supereruptions. What makes supervolcanoes particularly fascinating from a scientific perspective is their cyclical nature and the long periods of dormancy between major eruptions. Unlike typical volcanoes that might erupt every few years or decades, supervolcanoes operate on timescales that dwarf human civilization. The intervals between major eruptions at Yellowstone, for example, range from about 600,000 to 800,000 years, periods so long that entire species evolve and go extinct in the intervals between eruptions. This long dormancy is key to understanding how supervolcanoes work. During the quiet periods, magma continues to accumulate in vast underground chambers, slowly building pressure over hundreds of thousands of years. The magma undergoes complex chemical changes during this long storage period, becoming increasingly rich in silica and dissolved gases. When the eruption finally occurs, the high gas content and silica-rich composition create explosions of extraordinary violence. The geological record reveals that supervolcanic eruptions have occurred repeatedly throughout Earth's history, though they're rare enough that the intervals between them span many human lifetimes. The Campanian ignimbrite eruption in Italy, about 40,000 years ago, the various eruptions of the Taupo volcanic zone in New Zealand, and the ancient eruptions of the Valles caldera in New Mexico all represent supervolcanic events that significantly impacted regional and global environments. Living on borrowed time, the knowledge that supervolcanoes exist and that they will inevitably erupt again raises profound questions about human civilization's relationship with geological time. From a human perspective, The long intervals between supereruptions make them seem almost theoretical, events so rare and distant that they barely register in our planning and consciousness. Yet from a geological perspective, we're living in a period between eruptions, and the next supervolcanic event is not a question of if but when. Modern monitoring of the Yellowstone system provides fascinating insights into the behavior of a dormant supervolcano. Scientists track ground deformation using GPS and satellite measurements, monitor earthquake activity throughout the region, and analyze the chemistry of gases emitted by hot springs and fumaroles. These studies reveal that the Yellowstone magma chamber is still very much active, with ongoing processes of magma injection, crystallization, and gas release occurring deep beneath the surface. The ground at Yellowstone rises and falls by centimeters over periods of years, reflecting the breathing of the magma chamber below. Earthquake swarms periodically shake the region as magma movements adjust stress patterns in the surrounding rock. The hot springs show chemical changes that may reflect evolving conditions in the deep magma system. All of these observations confirm that Yellowstone is not extinct but merely dormant, resting between periods of activity and cycles that span geological ages. The global impact of ash and climate. One of the most sobering aspects of supervolcanic eruptions is their potential for global impact through atmospheric effects. When supervolcanoes erupt, they inject enormous quantities of ash, sulfur compounds, and other gases into the stratosphere, where they can remain suspended for months or years. These particles and gases can have profound effects on global climate, potentially causing short-term cooling that affects agriculture, ecosystems, and human societies worldwide. Computer models of potential future supervolcanic eruptions suggest that a Yellowstone-scale event could reduce global temperatures by several degrees Celsius for several years, drastically affecting agricultural productivity in many regions. The ash fallout could disrupt transportation, contaminate water supplies, and cause respiratory health problems over areas covering multiple continents. The economic and social disruptions could cascade through interconnected global systems in ways that are difficult to predict, but potentially catastrophic in scale. Yet for all their potential for destruction, supervolcanoes also represent some of the most creative forces in Earth's geological history. The massive amounts of new volcanic material they produce create new landforms and provide fresh mineral resources. The climatic disruptions they cause, while devastating in the short term, often trigger evolutionary changes that lead to new biodiversity in the long term. They're agents of both destruction and renewal on a planetary scale. The deep rhythms of Earth. As you settle deeper into the peaceful transition towards sleep, let yourself contemplate the profound humility that comes from understanding supervolcanoes. These events remind us that we live on a planet whose deepest rhythms operate on timescales that dwarf human experience. The ground beneath our feet, so seemingly solid and permanent, is actually part of dynamic systems that operate according to geological time. The Yellowstone region that today hosts millions of visitors each year has been repeatedly destroyed and rebuilt by supervolcanic eruptions. The peaceful lakes and forests are temporary features in a landscape that is periodically erased and rewritten by forces of almost unimaginable power. Yet these same forces are part of what makes Earth a dynamic living planet capable of supporting the rich diversity of life we see today. Supervolcanoes teach us that destruction and creation are not separate processes, but different aspects of the same planetary systems that have shaped Earth for billions of years. The ash that buries forests also creates the fertile soils that will support future forests. The climatic disruptions that challenge existing species also create opportunities for new evolutionary experiments. Even the most catastrophic events in Earth's history have ultimately contributed to the planet's long-term capacity to support life. In the gentle darkness as consciousness fades towards sleep, these sleeping giants continue their patient accumulation of molten rock, their slow building toward distant futures when they will once again reshape the world. They remind us that we are temporary guests on a planet whose story is written in fire and stone, in processes that connect the deepest interior of the Earth to the farthest reaches of the atmosphere, in cycles of destruction and renewal that continue regardless of human presence or awareness. The next time you see a peaceful landscape, a quiet forest, a placid lake, a rolling meadow, remember that you may be looking at the dormant stage of geological forces that can reshape continents. In the silence of these sleeping giants lies the patient power that has built and rebuilt our world countless times, and that continues even now to write the next chapters in Earth's eternal story of fire and renewal. Where fire meets ice, the paradox of volcanic winters. As your breathing deepens and your mind drifts toward the threshold of dreams, let's explore one of nature's most fascinating contradictions, the places where volcanic fire and glacial ice coexist, creating landscapes and phenomena that seem to defy the very laws of nature. In these remarkable environments, the fundamental forces of heat and cold, creation and preservation, violence and stillness, come together to produce some of the most spectacular and scientifically significant features on our planet. The marriage of fire and ice might seem impossible. After all, don't these elements naturally oppose each other? Yet across the globe, from the glaciated peaks of Iceland to the ice-covered volcanoes of Antarctica, we find places where molten rock and frozen water have learned to coexist in ways that transform both, creating unique landscapes that exist nowhere else in the natural world. Perhaps no place on Earth demonstrates this paradox more dramatically than Iceland, the island nation that sits astride the mid-Atlantic ridge and experiences some of the most intense volcanic activity on the planet, while also being home to massive glaciers and ice caps. Here, fire and ice don't simply coexist, they actively collaborate in creating phenomena that reshape the landscape in ways that neither could achieve alone. Subglacial eruptions. When fire meets frozen water. When a volcano erupts beneath a glacier, the result is unlike any other type of volcanic activity. Instead of the familiar sight of lava fountains shooting into the air, subglacial eruptions begin invisibly, as magma encounters ice kilometers thick and millions of tons in weight. The initial contact between molten rock at temperatures exceeding 1000 degrees Celsius and ice at temperatures well below freezing creates an explosive interaction that generates enormous amounts of steam and meltwater. These subglacial eruptions follow a distinctive pattern. First, the heat from rising magma creates a cavity within the glacier, melting ice to form a lake of water trapped beneath hundreds of meters of ice. As the eruption continues, more ice melts, and the volume of trapped water grows. Eventually, the pressure becomes too great for the ice to contain, and the water bursts forth in what Icelanders call a jökullaup, a glacial outburst flood of almost unimaginable power. These jökullaups can carry flows of water that rival the Amazon River, but lasting for only hours or days. They carry not just water, but enormous blocks of ice, volcanic debris, and sediment, carving new valleys and reshaping landscapes with the combined power of volcanic heat and glacial ice. The 1996 eruption of Grímsvötn volcano beneath Iceland's Vatnajökull glacier created a jökullaup that carried 45,000 cubic meters of water per second, a flow rate that temporarily made it one of the largest rivers in the world. Tuyas, mountains born of ice and fire. One of the most distinctive landforms created by subglacial volcanism is the Tuya, a flat-topped, steep-sided volcanic mountain that records the history of eruptions beneath ice. These geological monuments tell the story of volcanic fire, constrained and shaped by glacial ice, in ways that create landforms unlike anything formed by conventional volcanism. The formation of a tuya begins with eruptions on the floor of a glacier or ice sheet. As magma encounters ice, it cools rapidly, forming pillow lavas and volcanic glass. But because the eruption is confined beneath ice, the volcanic products pile up in a contained space rather than spreading widely as they would in subaerial eruptions. As the eruption continues, the pile of volcanic material grows higher, gradually approaching the level of the ice surface. When the volcanic pile finally reaches the top of the ice, the character of the eruption changes dramatically. No longer constrained by ice, the lava can spread horizontally, forming a flat cap on top of the steep-sided pile of subglacial volcanic products. The result is a distinctive flat-topped mountain that preserves the record of its birth beneath ice for millions of years after the ice itself has disappeared. Iceland is home to numerous tuas, each telling its own story of fire and ice. These mountains provide scientists with detailed records of past ice thicknesses and volcanic activity, serving as geological libraries that preserve information about ancient climates and volcanic processes. Some tuas in Iceland show evidence of multiple episodes of subglacial eruption, recording periods when ice advanced and retreated over the same volcanic centers. Antarctic volcanoes. Fire beneath the ice sheet. While Iceland provides the most accessible examples of fire-ice interactions, perhaps the most extreme examples occur in Antarctica, where more than 100 volcanoes lie hidden beneath the world's largest ice sheet. These volcanoes, most of them unknown until recent decades, represent one of the most remote and least understood volcanic systems on Earth. The West Antarctic Rift System contains numerous active volcanoes, some of which have erupted in recent years despite being buried beneath kilometers of ice. Mount Erebus, the southernmost active volcano on Earth, provides a spectacular exception. Its summit rises above the ice, and it maintains a permanent lava lake despite being surrounded by one of the harshest environments on the planet. But it's the hidden volcanoes that present the most intriguing scientific questions. When these buried volcanoes erupt, they create vast caverns of meltwater beneath the ice sheet, potentially lubricating the base of glaciers and affecting ice flow patterns on a continental scale. Some scientists suggest that volcanic heat from these hidden systems may be contributing to ice sheet instability in West Antarctica, with implications for global sea level rise. Recent research has revealed complex systems of subglacial lakes in Antarctica, some of which may be maintained by volcanic heat. These hidden bodies of liquid water, existing in permanent darkness beneath kilometers of ice, represent some of the most extreme and isolated environments on Earth. Yet they may harbor unique microbial communities that have evolved in complete isolation from the surface world, potentially providing insights into how life might exist in similar environments on other planets. The thermal oases of volcanic regions. Even in the most ice-dominated landscapes, volcanic heat creates pockets of warmth that can support life in otherwise sterile environments. In Iceland, geothermal areas maintain ice-free zones where specialized plant communities thrive throughout the harsh Arctic winter. These thermal oases, warmed by underground volcanic heat, provide refugia where species can survive during periods of extreme cold. The contrast between these warm zones and the surrounding ice creates dramatic ecological gradients over very short distances. Within meters, conditions can change from tropical warmth around hot springs to Arctic cold on nearby ice. These extreme gradients create unique evolutionary pressures and opportunities, leading to the development of specialized organisms adapted to life at the boundary between fire and ice. Some of these organisms have proven to be of immense scientific interest. Thermophilic bacteria living in volcanic hot springs in Iceland have provided insights into the origins of life and have applications in biotechnology and medicine. These organisms represent some of the most ancient forms of life on Earth, thriving in conditions that may be similar to those present when life first emerged billions of years ago. Glacial volcanism and climate. The interaction between volcanoes and ice has played important roles in Earth's climate system throughout geological history. During ice ages, when glaciers covered much larger areas than they do today, subglacial volcanism was much more common. The interaction between widespread ice and continuing volcanic activity created feedback loops that influence both local and global climate patterns. Volcanic eruptions beneath ice sheets can trigger rapid ice loss through melting and the lubrication of ice flow by meltwater. At the same time, the ice modifies volcanic eruptions, often making them more explosive and affecting the distribution of volcanic products. These interactions create complex feedback systems between the cryosphere and volcanic activity that scientists are still working to understand. The relationship between ice and volcanoes also extends to their effects on global climate. Large volcanic eruptions can inject sulfur compounds into the stratosphere, causing global cooling that can trigger ice age conditions. Conversely, the melting of ice sheets during periods of intense volcanic activity can affect ocean circulation and atmospheric patterns in ways that influence global climate. Ice caves and fumaroles. Architecture of extremes. Some of the most beautiful and ephemeral features created by fire-ice interactions are the ice caves that form around volcanic vents in glaciated regions. Volcanic heat melts tunnels and chambers within glaciers, creating temporary underground palaces of ice, illuminated by the otherworldly blue light that filters through glacial ice. These ice caves are constantly changing as volcanic heat waxes and wanes, and as glacial ice flows and deforms. Fumaroles, vents that emit volcanic gases, create particularly spectacular ice formations when they occur in glaciated environments. The hot volcanic gases melt the surrounding ice, but then freeze again when they mix with the frigid air, creating fantastic sculptures of ice that change daily or even hourly as conditions fluctuate. These ephemeral art installations, created by the collaboration between fire and ice, exist for brief moments in geological time before melting away and being replaced by new formations. The future of fire and ice. As you drift deeper into the peaceful state that precedes sleep, consider that the interaction between volcanic fire and glacial ice continues to evolve with changing global conditions. Climate change is causing glaciers to retreat worldwide, potentially exposing volcanoes that have been covered by ice for thousands of years. At the same time, the reduction in ice cover may alter volcanic behavior, as the removal of the weight of ice can affect magma production and eruption patterns. These changes will create new landscapes and new opportunities for scientific discovery. Volcanoes that have been hidden beneath ice for millennia may become accessible for the first time, providing new insights into subglacial volcanic processes. The retreat of glaciers may also reveal new evidence of past volcanic activity, helping scientists understand the long-term relationship between ice and fire. In the gentle transition towards sleep, let yourself appreciate the profound beauty of these places where seemingly opposite forces come together to create something entirely new. The landscapes shaped by fire and ice remind us that nature thrives on paradox, that the most spectacular phenomena often occur at the boundaries between different systems, and that even the most seemingly incompatible forces can collaborate to create wonders that neither could achieve alone. The next time you see images of volcanic eruptions or glacial landscapes, remember that in some remarkable places on our planet, these phenomena coexist and collaborate, creating temporary masterpieces of ice and steam, of fire and frozen water, of destruction and preservation happening simultaneously. These places remind us that Earth is a planet of infinite creativity, where the impossible becomes routine, and where fire and ice dance together in the eternal choreography of geological change. The hidden volcanic heart of the ocean, the greatest mountain range you'll never see. As your mind settles into the quiet rhythm that leads towards sleep, Let's embark on a journey to the most volcanically active places on Earth, places that few humans will ever visit, yet which produce more volcanic rock than all land-based volcanoes combined. These are the mid-ocean ridges, vast underwater mountain ranges that circle the globe like the seams on a baseball, hidden beneath kilometers of seawater, yet fundamentally shaping the world we live on. Imagine, if you can, a mountain range longer than all the continental mountain ranges combined, more than 60,000 kilometers of peaks, valleys, and volcanic landscapes stretching through every ocean on Earth. This underwater mountain system is not only the longest mountain range on the planet, but also the most volcanically active, continuously producing new oceanic crust through processes that have operated for hundreds of millions of years. Unlike the explosive, cone-building volcanism we see on land, the volcanism of the mid-ocean ridges is gentler, more continuous, and yet ultimately more productive. Here, in the perpetual darkness of the deep sea, molten rock wells up from the Earth's interior to create new seafloor at rates measured in centimeters per year. It's a process so slow that it would be imperceptible during a human lifetime, yet so persistent that it completely renews all the ocean floors every 200 million years or so. The assembly line of Earth's crust. The mid-ocean ridge system operates like a vast geological assembly line, continuously manufacturing new oceanic crust as tectonic plates slowly pull apart. As the plates separate, hot rock from the mantle rises to fill the gap, partially melting as it rises due to the decrease in pressure. This molten rock, or magma, reaches the seafloor and erupts as lava, cooling rapidly in contact with the frigid seawater to form new oceanic crust. But this isn't the dramatic, explosive volcanism we might imagine. Instead, it's a process of gentle oozing as molten rock flows out of cracks in the seafloor and cools almost instantly into distinctive pillow-shaped formations. These pillow lavas, formed when molten rock encounters cold water, create landscapes that are utterly unlike anything on land, endless fields of bulbous pillow-like forms stretching across the abyssal plains. The rate of crustal production varies along different parts of the ridge system, but the global average is about 3.4 square kilometers of new oceanic crust per year. To put this in perspective, that's equivalent to creating an area the size of Rhode Island every year, year after year, for hundreds of millions of years. The cumulative effect of this process has been to create all the oceanic crust that exists today, roughly 60% of Earth's surface. The architecture of ocean floor creation. The structure of mid-ocean ridges reflects the ongoing process of seafloor spreading. At the center of each ridge lies a rift valley, a deep depression where the actual volcanic activity occurs. This valley is typically 2 kilometers wide and several hundred meters deep, bounded by steep walls that rise toward the ridge crest on either side. Within the rift valley, volcanic activity is concentrated along the central axis, where networks of fissures allow magma to reach the seafloor. These fissures, some of them hundreds of meters long, serve as the primary conduits for volcanic eruptions. The eruptions themselves are typically brief but frequent, with lava flows spreading outward from the fissures to build up the seafloor layer by layer. As new volcanic material is added to the center of the ridge, older material is pushed outward on both sides, gradually moving away from the active rift zone. This conveyor belt process means that the age of oceanic crust increases with distance from the ridge axis. The oldest parts of the ocean floor, found near continental margins, can be up to 200 million years old, while the youngest parts at the ridge crests are essentially zero age. Black smokers and white smokers, undersea chimneys. Among the most spectacular features of the mid-ocean ridge system are the hydrothermal vents, underwater geysers that shoot superheated, mineral-rich water hundreds of meters into the cold abyssal depths. These vents, often called black smokers, or white smokers depending on the color of the minerals they precipitate, represent points where seawater penetrates deep into the newly formed oceanic crust, encounters hot volcanic rocks and returns to the surface laden with dissolved metals and other chemicals. The process begins when seawater seeps down through cracks in the volcanic rock, penetrating several kilometers into the oceanic crust. As it descends, the water encounters increasingly hot conditions, reaching temperatures of 400 degrees Celsius or more in the reaction zones around magma chambers. At these temperatures and under the extreme pressure of the deep ocean, the water becomes a powerful chemical solvent, leaching metals, sulfur compounds, and other minerals from the surrounding rocks. When this superheated, chemically enriched water finally erupts back onto the seafloor, the sudden change in temperature and pressure causes dissolved minerals to precipitate out almost instantly. Iron sulfides create the black smoke of black smoker vents, while lighter-colored minerals create the white plumes of white smokers. Over time, these precipitating minerals build up around the vents, creating towering chimneys that can grow several meters high within just a few years. These hydrothermal systems are not just geological curiosities. They're among the most biologically productive environments in the deep ocean. Despite the crushing pressure, extreme temperatures, and toxic chemical conditions, hydrothermal vents support thriving ecosystems based entirely on chemosynthesis rather than photosynthesis. Bacteria and archaea harvest energy from the chemical reactions between vent fluids and seawater, forming the base of food webs that include giant tube worms, ghostly crabs, and specialized fish. The global circulation system. The mid-ocean ridge system plays a crucial role in Earth's global circulation systems, both geological and oceanic. The continuous production of new oceanic crust at ridges is balanced by the destruction of old crust at subduction zones, where oceanic plates dive back into the mantle. This process, part of the broader system of plate tectonics, is responsible for the slow but continuous motion of continents across Earth's surface. The hydrothermal circulation associated with ridge volcanism also plays important roles in regulating ocean chemistry. The enormous volumes of seawater that circulate through the oceanic crust at ridge systems carry away heat from the Earth's interior while adding dissolved minerals and gases to the oceans. This hydrothermal flux affects the chemical composition of seawater on a global scale, influencing everything from the pH of the oceans to the availability of nutrients that support marine life. Recent research has revealed that hydrothermal systems may also play important roles in global climate regulation. The carbon dioxide released by submarine volcanic activity contributes to oceanic carbon cycles, while the precipitation of carbonate minerals at some hydrothermal sites removes carbon from the ocean atmosphere system. These processes operate on geological timescales but may influence long-term climate patterns. Magnetic stripes, the tape recorders of Earth history. One of the most elegant discoveries in Earth science came from studying the magnetic properties of oceanic crust, formed at mid-ocean ridges. As lava cools and solidifies at ridge crests, magnetic minerals in the rock become aligned with Earth's magnetic field at the time of formation. But Earth's magnetic field periodically reverses, with magnetic north becoming magnetic south and vice versa. This process has created a remarkable record preserved in the oceanic crust, alternating stripes of normal and reversed magnetic polarity that spread outward from ridge crests like a magnetic tape recording of Earth's magnetic field history. These magnetic anomaly patterns provided crucial evidence for the theory of seafloor spreading and plate tectonics, demonstrating that the ocean floors are indeed spreading outward from central ridges. The magnetic striping patterns also provide a precise tool for dating oceanic crust and measuring spreading rates. By comparing the magnetic anomaly patterns on opposite sides of ridges, scientists can determine how fast the seafloor has been spreading and how this rate has changed over time. This technique has revealed that spreading rates vary considerably, from less than 2 centimeters per year at slow-spreading ridges to more than 20 centimeters per year at the fastest-spreading ridges. Life in the abyss. The discovery of hydrothermal vent ecosystems at mid-ocean ridges revolutionized our understanding of life on Earth. Before the first direct observations of these systems in the 1970s, scientists assumed that the deep ocean was essentially a biological desert, sparsely populated by organisms dependent ultimately on organic matter produced by photosynthesis in surface waters. The reality proved far more remarkable. Hydrothermal vents support some of the most productive ecosystems on Earth, rivaling tropical rainforests in their biological activity, despite existing in perpetual darkness under crushing pressure. These ecosystems are based on chemosynthetic bacteria that derive energy from chemical reactions rather than sunlight, demonstrating that life can thrive in environments completely divorced from solar energy. The organisms living around hydrothermal vents have evolved remarkable adaptations to extreme conditions. Giant tube worms lack digestive systems entirely, instead harboring symbiotic bacteria in their bodies that convert chemical energy into organic matter. Vent crabs have modified hemoglobin that can function in the low oxygen, high sulfide conditions around vents. Some fish species have antifreeze proteins that allow them to survive in the variable temperature conditions around active vents. The planetary perspective. As you drift closer to the edge of sleep, consider the profound implications of these hidden volcanic systems for our understanding of Earth as a planetary system. The mid-ocean ridges represent the most direct connection between Earth's deep interior and its surface environments. The heat they release, the chemicals they add to the oceans, and the new crust they produce all contribute to making Earth the dynamic, habitable planet we know. Without the continuous volcanic activity at mid-ocean ridges, Earth would be a very different place. The oceans would be chemically stagnant, lacking the mineral inputs that support marine productivity. The continents would be static, frozen in place without the plate tectonic motions driven by seafloor spreading. Even the atmosphere would be different, lacking the volcanic gases that help regulate global climate over geological time. The mid-ocean ridge system also provides our best model for understanding how similar processes might operate on other planets. Mars shows evidence of ancient rifting and possible seafloor spreading, while some of the icy moons of Jupiter and Saturn may have active hydrothermal systems beneath their frozen surfaces. By studying Earth's hidden volcanic heart, we gain insights into planetary processes that may be operating throughout the solar system. In the gentle darkness as consciousness fades towards sleep, these underwater volcanoes continue their patient work, building new seafloor grain by grain, pillow by pillow, eruption by eruption. They remind us that the most important geological processes often occur out of sight, in places where humans rarely venture, but where the fundamental architecture of our planet is continuously renewed. The next time you look out at the ocean, remember that beneath those waves lies the most volcanically active region on Earth, a hidden realm where fire and water collaborate to build the very foundations of our world. In the darkness of the deep sea, far from human observation, Earth's volcanic heart beats steadily on, creating the crust we stand on and maintaining the dynamic balance that keeps our planet alive and habitable. The Ring of Fire, where Earth's power converges. The circle of geological violence. As your mind drifts into the deeper currents of approaching sleep, let's journey to the most geologically active region on our planet, a vast horseshoe-shaped zone of volcanism and seismic activity that encircles the Pacific Ocean like a fiery necklace. This is the Ring of Fire, home to more than 75% of the world's active volcanoes and the site of roughly 90% of the world's earthquakes. Here, along the edges of the Pacific Plate, the forces that shape our planet converge with an intensity found nowhere else on Earth. The Ring of Fire stretches for more than 40,000 kilometers, beginning at the southern tip of South America, running northward along the western coasts of South and North America, then arcing westward through the Aleutian Islands of Alaska, south through the Kamchatka Peninsula of Russia, Japan, the Philippines, Indonesia, and finally southward through New Zealand. This immense arc represents the boundary zones where the Pacific Plate meets and interacts with the surrounding continental and oceanic plates, creating a zone of almost constant geological activity. To understand why this region is so volcanically active, we must picture the Pacific Plate as a vast raft of oceanic crust, slowly moving across the Earth's surface. As this plate encounters the edges of surrounding continents, it typically dives beneath them in a process called subduction. As the oceanic crust descends into the hot mantle, it begins to melt, generating the magma that feeds the volcanoes of the Ring of Fire. The subduction factory. The volcanic activity along the Ring of Fire is fundamentally different from the gentle, continuous volcanism of mid-ocean ridges. Here, volcanism is driven by subduction, the process by which dense oceanic crust dives beneath lighter continental crust, carrying with it seawater, marine sediments and oceanic rocks that have never before experienced the extreme temperatures and pressures of the Earth's interior. As the subducting oceanic plate descends, it undergoes a complex series of physical and chemical changes. The increasing temperature and pressure cause minerals in the oceanic crust to break down and release water and other volatile compounds. This water, when added to the hot rocks of the overlying mantle, dramatically lowers their melting point, causing large volumes of rock to melt and form magma. But this subduction-generated magma is different from the basaltic magma produced at mid-ocean ridges. It's typically more silica-rich and contains more dissolved gases, making it more viscous and more prone to explosive eruptions. When this gas-rich magma reaches the surface, it often erupts with tremendous violence, creating the towering volcanic peaks and devastating explosive eruptions that characterize the Ring of Fire. The process is like a vast geological recycling system, where old oceanic crust is consumed at subduction zones, while new crust is simultaneously being created at mid-ocean ridges. The Ring of Fire represents the consumption side of this equation, the places where oceanic plates return to the mantle, releasing their chemical components in spectacular volcanic displays that have shaped the geology and geography of the Pacific Rim for hundreds of millions of years. The cascade of volcanoes. Along the western coast of North America, the subduction of the Wanda Fuca Plate beneath the North American plate has created the Cascade Range, a chain of volcanic peaks that includes some of the most iconic and dangerous volcanoes in North America. Mount Rainier, Mount Hood, Mount Shasta, and Mount St. Helens are all products of this ongoing subduction process, each representing a point where magma generated by the descending oceanic plate has found its way to the surface. Mount St. Helens, which erupted catastrophically in 1980, provides a dramatic example of Ring of Fire volcanism in action. The eruption began with a massive landslide that removed the entire north face of the mountain, followed by a lateral blast that devastated more than 500 square kilometers of forest. The ash cloud reached the stratosphere and circled the globe, while pyroclastic flows, hot avalanches of gas, ash, and rock, raced down the mountainsides at speeds exceeding 100 kilometers per hour. But the 1980 eruption, devastating as it was, represents just one moment in the ongoing geological story of the Cascades. Each of these volcanoes has erupted repeatedly throughout geological history, building their towering peaks through countless cycles of explosive activity. Mount Rainier, the tallest of the Cascade volcanoes, has been built up over hundreds of thousands of years of eruptions, and its massive bulk, visible from Seattle on clear days, serves as a reminder that this volcanic activity continues beneath the seemingly peaceful snow-capped summit. The Japanese archipelago, born of fire. Perhaps nowhere in the Ring of Fire is the relationship between subduction and volcanism more dramatically displayed than in Japan, where the Pacific Plate and Philippine Sea Plate dive beneath the Japanese islands, creating one of the most volcanically active regions on Earth. Japan is home to more than 100 active volcanoes, and volcanic eruptions are so common that they're woven into the cultural and spiritual fabric of Japanese society. Mount Fuji, Japan's most famous volcano and a sacred mountain in Japanese culture, exemplifies the beauty and danger of Ring of Fire volcanism. This nearly perfect volcanic cone, rising 3,776 meters above sea level, has been built through countless eruptions over the past 100,000 years. Its last major eruption, in 1707, deposited ash as far away as Tokyo, more than 100 kilometers to the northeast, demonstrating the far-reaching effects that even moderate Ring of Fire eruptions can have. But Fuji is just one of many active volcanoes in Japan. The country experiences dozens of volcanic eruptions each year, ranging from gentle emissions of gas and steam to violent explosive eruptions that threaten nearby populations. The Japanese have developed sophisticated monitoring systems and evacuation procedures, recognizing that living in the Ring of Fire requires constant vigilance and preparedness. Indonesian Fire Mountains. Indonesia, an archipelago of more than 17,000 islands, sits at one of the most geologically complex parts of the Ring of Fire, where multiple tectonic plates converge and interact. The country is home to more active volcanoes than any other nation, 127 at last count, and volcanic activity has played a fundamental role in shaping both the physical landscape and human history of the region. The 1815 eruption of Mount Tambora in Indonesia was one of the most powerful volcanic eruptions in recorded history, ejecting so much ash and sulfur dioxide into the atmosphere that it caused global climate anomalies for several years. The eruption killed more than 70,000 people directly, but its climatic effects may have killed many more through crop failures and famine around the world. The year 1816 became known as the year without a summer in Europe and North America, as volcanic particles in the atmosphere blocked sunlight and caused widespread agricultural failures. More recently, the 1883 eruption of Krakatoa, also in Indonesia, demonstrated the global reach of Ring of Fire volcanism. The explosion was heard as far away as Australia and Mauritius, distances of thousands of kilometers. The volcanic ash circled the globe multiple times, creating spectacular sunsets for months afterward. Tsunamis generated by the eruption killed more than 36,000 people in coastal areas around the Java Sea. The Andes, the longest volcanic chain. The western coast of South America hosts the longest continuous chain of volcanoes in the Ring of Fire, the Andes Mountains, which stretch for more than 7,000 kilometers from Venezuela to Chile. This massive mountain range has been built primarily through subduction-related volcanism, as the oceanic Nazca Plate dives beneath the South American continent, generating the magma that feeds hundreds of active volcanoes. The Andes contain some of the highest volcanoes on Earth, with several peaks exceeding 6,000 meters in elevation. These high-altitude volcanoes present unique challenges for both scientific study and hazard monitoring, as their remote locations and extreme elevations make them difficult to access and instrument. Yet they continue to erupt regularly, sometimes with devastating consequences for the communities that have developed in their shadows. The 1985 eruption of Nevado del Ruiz in Colombia tragically demonstrated how even relatively small volcanic eruptions can have catastrophic consequences in populated areas. The eruption melted glacial ice on the volcano's summit, generating massive mudflows called lahars that raced down river valleys at speeds of up to 60 kilometers per hour. The town of Armero, located 74 kilometers from the volcano, was completely buried by these mudflows, killing more than 23,000 people in one of the deadliest volcanic disasters in recorded history. Living with fire. What makes the Ring of Fire particularly significant from a human perspective is that it includes some of the most densely populated regions on Earth. Hundreds of millions of people live within the potential impact zones of Ring of Fire volcanoes, drawn by the fertile soils that volcanic activity creates but vulnerable to the periodic eruptions that are an inevitable consequence of this geological setting. The relationship between human populations and Ring of Fire volcanism is complex and often paradoxical. The same subduction processes that generate dangerous explosive eruptions also create the conditions for extraordinary soil fertility. Volcanic ash weathers quickly in tropical climates, releasing nutrients that support intensive agriculture. Many of the world's most productive agricultural regions, from the coffee plantations of Central America to the rice terraces of Java, exist because of the fertility that volcanic activity provides. This creates a fundamental dilemma for human societies in the Ring of Fire. The volcanic processes that make these regions productive and habitable also make them dangerous. Communities must balance the benefits of living in volcanically active areas against the risks of periodic eruptions, developing strategies for monitoring volcanic activity, preparing for eruptions, and recovering from their inevitable impacts. The Pacific Plate's journey. The Ring of Fire exists because the Pacific Plate is simultaneously the largest and most mobile of Earth's tectonic plates, constantly colliding with and diving beneath the smaller plates that surround it. This oceanic plate, roughly 103 million square kilometers in area, has been moving northwestward for tens of millions of years, carrying with it a record of volcanic activity preserved in seamount chains, oceanic plateaus, and other volcanic features. The Hawaiian Emperor Seamount Chain, for example, records the Pacific Plate's motion over a stationary hotspot in the mantle. As the plate moved northwestward, it carried older Hawaiian islands away from the hotspot, while new islands formed in their place, creating a chain of volcanic islands and seamounts that stretches for thousands of kilometers across the Pacific Ocean. This plate motion is part of what drives the Ring of Fire's intense activity. As the Pacific Plate continues its northwestward journey, it constantly creates new subduction zones while modifying existing ones, ensuring that the Ring of Fire will remain geologically active for millions of years to come. The Whisper of Ancient Fire. As twilight settles over your thoughts and the day's worries begin to fade, imagine yourself drifting on a cloud of warm volcanic ash, not the dangerous kind, but the microscopic particles that have traveled thousands of miles, cooled and gentled by their journey through the atmosphere. These tiny fragments carry within them the chemical signatures of distant eruptions, each grain a messenger from the Earth's molten heart, now soft as powder against your consciousness. Let your mind wander to a world where mountains breathe in geological time, where the very ground beneath our feet pulses with the slow, steady heartbeat of a living planet. Tonight, we'll explore not just the Ring of Fire, but the entire symphony of volcanic processes that have shaped our world, and countless others, across billions of years of cosmic evolution. The molecular dance of creation. In the drowsy comfort of approaching sleep, consider the extraordinary molecular choreography happening miles beneath your feet, deep in the Earth's mantle, at temperatures that would instantly vaporize any earthly material. Silicon and oxygen atoms are locked in an eternal dance. These aren't the violent collisions we might imagine, but rather a stately waltz performed over millions of years, as convection currents carry molten rock in grand sweeping patterns that span entire continents. The mantle itself is a marvel of physics, neither fully solid nor truly liquid, but something wonderfully in between, like cosmic honey heated to unimaginable temperatures. Here, at depths where the pressure reaches 140,000 times that of our gentle atmospheric blanket, crystals of olivine and pyroxene slowly dissolve and reform, their atomic structures rearranging in response to temperature gradients that shift over geological epochs. When these superheated materials finally breach the surface as magma, They carry with them a chemical library of Earth's deep history. Each volcano's eruption is like opening an ancient book written in elements, strontium isotopes that reveal the age of the rock, rare earth elements that speak of cosmic processes, and noble gas signatures that whisper of the planet's earliest atmosphere, preserved in crystalline time capsules for billions of years. The process of subduction, where oceanic plates slide beneath continental masses, is perhaps nature's most elegant recycling system. Picture massive slabs of oceanic crust, laden with sediments that once danced as plankton in prehistoric seas, slowly descending into the mantle's embrace. As they sink, carrying their cargo of ancient carbon, water, and organic compounds, they begin to release volatile substances at precise depths and temperatures, a process so finely tuned that it maintains Earth's delicate atmospheric balance. At depths of 100 kilometers, water locked in crystalline structures begins to escape, reducing the melting point of surrounding rock like salt on ice. The resulting partial melts are chemically distinct from their source materials, enriched in elements that prefer to remain liquid: potassium, silicon, aluminum, creating the diverse spectrum of volcanic rocks that paint our landscapes in subtle variations of grey, black, and russet. This is not random violence, but exquisite precision. The Earth's interior operates like a vast chemical laboratory, sorting elements by their electrical charges and atomic radii, concentrating rare minerals in specific zones, and timing their release to the surface with clockwork precision that spans millions of years. When you see a volcano erupting, you're witnessing the culmination of processes that began when dinosaurs roamed the Earth, or even earlier. The magnetic field signatures locked within volcanic rocks tell us even more remarkable stories. As lava cools and solidifies, iron-bearing minerals align themselves with Earth's magnetic field like tiny compass needles frozen in time. By studying these paleomagnetic records, scientists have discovered that our planet's magnetic poles have reversed hundreds of times throughout history, creating a striped pattern across the ocean floors that reads like a geological barcode of deep time. The breathing of continents. As your breathing slows and deepens, matching the gentle rhythm of sleep, imagine the continents themselves breathing, not with the quick inhalation and exhalation of living lungs, but with the measured eternal breath of geological time. Each breath cycle spans millions of years, and the exhalation comes in the form of volcanic emissions that have shaped not just the land, but the very composition of our atmosphere and oceans. The Ring of Fire is just one verse in this planetary breathing song. Stretching like a necklace of glowing pearls around the Pacific Ocean, it represents the most dramatic manifestation of our planet's internal energy reaching the surface. But to truly understand this magnificent system, we must dive deeper into the quantum mechanics of crystal formation, the thermodynamics of phase transitions, and the beautiful chaos theory that governs how simple physical laws create patterns of breathtaking complexity. In the Cascade Range of North America, where Mount St. Helens dramatically reminded us of volcanic power in 1980, we find a perfect laboratory for understanding explosive volcanism. The chemistry here is subtle and fascinating. High silica magmas that trap gases like carbon dioxide and sulfur dioxide in a geological pressure cooker. As this magma rises through the crust, decompression causes dissolved gases to form bubbles, just like opening a bottle of champagne, but on a scale that can devastate hundreds of square kilometers. The pyroclastic flows that result from these explosive eruptions are marvels of fluid dynamics, behaving like dense atmospheric rivers that hug the ground at temperatures exceeding 800 degrees Celsius. Yet they follow the same mathematical principles that govern avalanches, turbidity currents in deep ocean trenches, and even the flow of granular materials in industrial processes. The physics is both universal and elegant: gravity, momentum, and friction creating patterns that repeat across scales from laboratory experiments to planetary catastrophes. Traveling south along the Ring of Fire to the Andes Mountains, we encounter a different variety of volcanic behavior, shaped by the unique geometry of plate convergence. Here, the Nazca Plate slides beneath the South American continent at an angle so precise that it creates a chain of stratovolcanoes spaced with mathematical regularity. The magma chemistry changes systematically along this chain, from basaltic compositions near the coast to increasingly evolved, differentiated magmas toward the continental interior, a natural experiment in igneous petrology spanning thousands of kilometers. The high-altitude environment of Andean volcanoes creates unique conditions where atmospheric pressure is so low that water boils at temperatures cool enough to touch. This affects not just the style of eruptions but the very chemistry of volcanic gases. At elevations above 4,000 meters, volcanic lakes can exist at temperatures that would be impossible at sea level, creating ethereal landscapes where chemistry and physics bend the rules of our everyday experience. In Japan, where the Pacific Plate subducts beneath the Philippine Sea Plate, which itself subducts beneath the Eurasian Plate, we find volcanic complexity that would challenge the most sophisticated computer models. This triple junction creates a three-dimensional puzzle of magma generation, where different chemical signatures mix and mingle to produce some of the most diverse volcanic rocks on Earth. Mount Fuji's perfect symmetry belies this underlying complexity. Its conical shape results from thousands of years of strombolian eruptions, each one depositing layers of tephra and lava with the precision of a master sculptor. The Japanese archipelago also demonstrates how volcanic activity couples with climate systems in ways both subtle and profound. The Sea of Japan, partially enclosed by volcanic arcs, creates unique oceanographic conditions that affect everything from precipitation patterns to the distribution of marine ecosystems. Underwater volcanic activity here contributes dissolved minerals to seawater, supporting unique chemosynthetic communities around hydrothermal vents. Moving further into the Western Pacific, the Indonesian archipelago presents perhaps the most volcanically active region on Earth, where over 130 active volcanoes define the landscape. This is where the Indo-Australian Plate collides with the Eurasian Plate along a complex suture zone that has been active for over 50 million years. The resulting volcanic diversity is staggering, from the sulfur-rich crater lakes of Java to the submarine volcanoes of the Banda Sea, each system adapted to specific pressure, temperature, and chemical conditions. The 1815 eruption of Mount Tambora in this region provides a masterclass in how volcanic systems can affect global climate through stratospheric chemistry. The sulfur dioxide ejected during this eruption reacted with stratospheric water vapor to form sulfuric acid aerosols that persisted for years, scattering incoming solar radiation and cooling global temperatures by more than 1 degree Celsius. This seemingly small change triggered crop failures across the northern hemisphere, demonstrating how local geological events can cascade into global environmental and social consequences. The chemical symphony of deep time. In the peaceful transition towards sleep, let your consciousness drift deeper into the molecular realm where volcanic processes reveal their most intimate secrets. At the scale of individual atoms and crystals, volcanic systems operate with a precision that rivals the most sophisticated chemical synthesis laboratories, creating minerals and compounds that exist nowhere else in nature. Consider the crystalline structures that form as magma cools, not random aggregations of matter, but highly ordered arrangements governed by fundamental laws of chemistry and physics. Feldspar crystals, the most abundant minerals in volcanic rocks, grow in triclinic and monoclinic symmetries that reflect the precise spacing of silicon and aluminum atoms. These atomic architectures determine not just the appearance of volcanic rocks, but their mechanical properties, their resistance to weathering, and even their electrical conductivity. The trace element chemistry of volcanic rocks reads like a periodic table written in stone. Rare earth elements such as neodymium and samarium, substitute for more common elements in crystal lattices with selectivity ratios determined by ionic radii and electrical charge. These substitutions occur with mathematical precision, following distribution coefficients that allow geochemists to calculate the pressure and temperature conditions of magma formation with remarkable accuracy. Zircon crystals, often no larger than grains of sand, preserve chemical information spanning billions of years. These tiny time capsules incorporate uranium atoms into their crystal structures, which then decay to lead at rates so constant they serve as atomic clocks. Some zircon grains found in volcanic rocks have revealed that continental crust existed on Earth more than 4 billion years ago, pushing back the timeline for when our planet first developed the chemical complexity necessary for life. The isotopic signatures of volcanic gases provide even more detailed information about Earth's chemical evolution. Helium-3, a primordial isotope trapped in the mantle since planetary formation, escapes to the surface through volcanic emanations at rates that tell us about the structure and convection patterns of Earth's deep interior. The ratio of helium-3 to helium-4 in volcanic gases varies systematically around the globe, creating a chemical map of mantle heterogeneity that extends down to the core mantle boundary. Volcanic sulfur compounds demonstrate how biological and geological processes interweave across deep time. The hydrogen sulfide and sulfur dioxide released during eruptions undergo complex photochemical reactions in the atmosphere, eventually returning to the surface as sulfuric acid that weathers volcanic rocks to release nutrients essential for plant growth. This sulfur cycle, mediated by volcanic activity, has operated for billions of years, helping to regulate both atmospheric composition and soil chemistry. The carbonatite volcanoes of East Africa represent one of nature's most unusual chemical factories, erupting magmas composed primarily of carbonate minerals rather than silicate rocks. These rare volcanic systems concentrate elements like niobium, tantalum, and rare earth elements to levels found nowhere else on Earth. The chemistry that creates these unusual magmas involves the dissolution of ancient organic matter in subducting plates, a process that directly links the carbon cycle to volcanic activity across geological time. Water plays a crucial role in volcanic chemistry that goes far beyond simple steam production. At the molecular level, water molecules dissociate under the extreme conditions within magma chambers, releasing hydrogen ions that affect the oxidation state of iron and other transition metals. This, in turn, influences the color, magnetic properties, and crystal structure of resulting volcanic minerals. The deep red of some volcanic glasses results from iron existing in specific oxidation states determined by the precise water content of the parent magma. The noble gases, helium, neon, argon, krypton, and xenon, provide the most direct chemical link between volcanic processes and the formation of our solar system. These chemically inert elements cannot be altered by weathering, biological processes, or most geological reactions, so their isotopic ratios in volcanic gases preserve signatures from the solar nebula, planetary accretion, and early atmospheric evolution. Xenon isotopes in particular tell a complex story of how Earth's atmosphere evolved through interactions between volcanic outgassing, solar wind stripping, and impacts from comets and asteroids. The chemistry of volcanic glasses reveals rapid cooling processes that preserve non-equilibrium mineral assemblages impossible to create in laboratory experiments. These natural glasses, particularly obsidian, exhibit molecular structures that exist in metastable states, technically unstable but kinetically prevented from changing over human timescales. At the atomic level, these glasses represent frozen snapshots of high-temperature chemical processes, providing unique insights into the dynamics of magma emplacement and cooling. The quiet mechanics of planetary engineering. As drowsiness envelops your thoughts like a warm volcanic hot spring, contemplate the elegant mechanical systems that drive volcanic processes across our planet. These are not crude engines of destruction, but sophisticated mechanisms of planetary engineering that operate with precision and purpose across scales from atomic to continental. The concept of isostatic equilibrium reveals how Earth's crust floats on the underlying mantle like icebergs in water, constantly adjusting its elevation in response to changing loads. When volcanoes build massive edifices like Mauna Loa in Hawaii, their weight actually depresses the underlying oceanic crust, creating a shallow depression that affects regional gravity fields. This depression, in turn, influences the pathways of subsequent magma ascent, creating a feedback system between volcanic loading and magma transport that operates over millions of years. The mechanics of magma chamber formation involve principles of structural geology and fluid dynamics that create natural laboratories for studying extreme materials science. As magma accumulates at depth, it heats and weakens surrounding rock, creating spherical or ellipsoidal chambers whose shapes are determined by the balance between magma pressure and lithostatic stress. The walls of these chambers undergo continuous thermal cycling, expanding and contracting in response to temperature variations that can exceed several hundred degrees Celsius. Ring dike systems, the circular fractures that often form around large volcanic centers, represent solutions to complex stress problems in three-dimensional space. These structures form when the roof of a magma chamber becomes too heavy to support itself, creating radial tensile stresses that focus along cylindrical surfaces. The resulting geometry is so predictable that engineers use similar principles in designing pressure vessels and other containment systems. The ascent of magma through the crust follows well-established principles of fluid mechanics, but under conditions so extreme that they push the boundaries of our physical understanding. Magma viscosity varies by more than 10 orders of magnitude, depending on temperature and chemical composition, ranging from fluids less viscous than water to materials more resistant to flow than cold honey. This viscosity controls everything from eruption style to the formation of different volcanic landforms. Volatile exsolution, the process by which dissolved gases separate from magma as it rises and depressurizes, follows Henry's law and other thermodynamic principles, but creates feedback mechanisms that can transition gradually ascending magma into explosive eruptions within minutes or hours. The nucleation and growth of gas bubbles in magma follows the same physical principles that govern bubble formation in carbonated beverages, but at temperatures and pressures that would instantly destroy any human-made materials. The seismic waves generated by volcanic processes provide detailed information about Earth's internal structure through natural experiments in wave propagation. P waves and S waves travel at different velocities through solid and molten materials, creating shadow zones and reflection patterns that reveal the three-dimensional structure of magma bodies. Modern seismic arrays can detect magma movements at depths of several kilometers, tracking the migration of melt from deep sources to shallow storage zones. Ground deformation associated with volcanic activity demonstrates how solid Earth materials respond to fluid pressure changes over timescales ranging from minutes to decades. The inflation and deflation of volcanic edifices follows elastic and viscoelastic models that account for both instantaneous and time-dependent deformation. These mechanical responses are so predictable that geodetic measurements can detect magma intrusions days or weeks before they reach the surface. The thermal mechanics of lava flows create natural laboratories for studying heat transfer in extreme environments. The formation of pahor and Aha lava textures results from different cooling rates and stress regimes that can be modeled using principles of materials science and fluid mechanics. The ropey textures of pahor lavas form through Kelvin-Helmholtz instabilities at the boundary between flowing lava and its cooling crust, the same mechanism that creates wave patterns in flowing water. Columnar jointing in volcanic rocks demonstrates how thermal stress creates remarkably regular geometric patterns through purely physical processes. As lava cools and contracts, Tensile stresses develop perpendicular to cooling surfaces, creating fracture networks that minimize stress energy according to principles derived from fracture mechanics. The resulting hexagonal columns represent optimal solutions to three-dimensional stress distribution problems, similar to those solved by engineers designing composite materials and structural systems. The mechanical coupling between volcanic systems and regional tectonics creates feedback loops that influence both volcanic activity and earthquake patterns over geological time. Large volcanic loads can trigger local seismic activity by altering stress fields in underlying crust, while regional earthquakes can modulate volcanic activity by changing the permeability of magma pathways. These interactions operate across multiple timescales, from immediate triggering relationships to long-term correlations spanning thousands of years. The invisible rivers of heat and chemistry. In the gentle embrace of approaching sleep, envision the invisible rivers that flow beneath Earth's surface, not rivers of water, but streams of heat, chemistry, and electromagnetic energy that connect volcanic systems across continents and ocean basins. These hidden currents operate according to physical principles that govern everything from the aurora borealis to the formation of ore deposits deep underground. Heat flow from Earth's interior follows the fundamental laws of thermodynamics, but creates temperature gradients so steep that they challenge our everyday understanding of thermal processes. In areas of active volcanism, geothermal gradients can exceed 100 degrees Celsius per kilometer of depth, 10 times the normal rate. This intense heat flow drives hydrothermal circulation systems that can extend several kilometers into the crust, creating three-dimensional networks of hot water flow that redistribute chemical elements with surgical precision. The chemistry of hydrothermal systems demonstrates how water can become one of the most powerful geological agents on Earth when heated beyond its normal boiling point. Under pressure, water remains liquid at temperatures exceeding 400 degrees Celsius, becoming a universal solvent capable of dissolving minerals that are completely insoluble under surface conditions. These superheated waters leach elements from volcanic rocks with selectivities determined by complex equilibria between multiple solid and aqueous phases. Hydrothermal ore deposits form through processes that represent natural examples of advanced hydrometallurgy, concentrating metals like gold, silver, copper, and molybdenum to levels thousands of times higher than their average crustal abundance. The precipitation mechanisms involve subtle changes in temperature, pressure, and chemical conditions that can concentrate trace elements into economically viable ore bodies. These same processes create the spectacular mineral diversity found around volcanic hot springs and fumaroles. The electromagnetic signatures of volcanic systems reveal hidden connections between Earth's magnetic field and subsurface fluid flow. Magnetotelluric surveys can detect variations in electrical conductivity associated with magma bodies and hydrothermal systems, mapping subsurface structures through their electromagnetic responses to natural variations in Earth's magnetic field. These techniques reveal that many volcanic regions are underlain by extensive networks of interconnected magma storage zones. Volcanic gas emissions create atmospheric chemistry laboratories that operate on scales from local to global. The sulfur compounds released during eruptions undergo complex photochemical reactions that produce aerosols with precisely controlled size distributions and chemical compositions. These volcanic aerosols serve as condensation nuclei for cloud formation, affecting precipitation patterns and atmospheric radiation balance in ways that can influence weather systems thousands of kilometers from their source. The carbon cycle mediated by volcanic activity represents one of Earth's most important long-term climate regulation mechanisms. Volcanic outgassing returns carbon dioxide to the atmosphere at rates that balance the slow removal of atmospheric CO2 by chemical weathering of silicate rocks. This carbonate-silicate cycle operates as a planetary thermostat, providing negative feedback that has maintained Earth's surface temperature within the narrow range necessary for liquid water over billions of years. Trace gas emissions from volcanoes include compounds that serve as natural tracers for atmospheric circulation patterns. Volcanic mercury, for example, can be detected in ice cores and sediments thousands of kilometers from its source, providing records of past volcanic activity that complement geological evidence. These chemical fingerprints allow scientists to reconstruct the history of major eruptions and their impacts on global atmospheric chemistry. The interaction between volcanic emissions and the stratosphere creates chemistry that affects the global ozone layer through catalytic reactions involving chlorine and bromine compounds. While these effects are generally small compared to anthropogenic ozone depletion, they demonstrate how local volcanic processes can influence atmospheric chemistry on a planetary scale. Some large eruptions inject enough halogen compounds into the stratosphere to cause measurable changes in ozone concentrations for several years. Volcanic systems also emit radon and other radioactive gases that provide unique insights into subsurface processes through their decay patterns and migration pathways. Radon emanometry. The study of radon emissions can detect changes in crustal permeability and fluid flow that precede volcanic eruptions by weeks or months. These natural radioactive tracers reveal how deeply volcanic systems extend into the crust and how they connect to regional groundwater systems. The thermal infrared signatures of volcanic systems demonstrate how heat radiates from Earth's surface according to blackbody radiation laws, but with spectral characteristics modified by volcanic gases and particles. Satellite-based thermal infrared monitoring can detect volcanic unrest through subtle changes in radiant temperature that precede visible signs of activity. These thermal anomalies often reveal the presence of shallow magma intrusions and hydrothermal circulation patterns that are invisible to other monitoring techniques. The crystalline libraries of deep time. As sleep's gentle tide carries away the day's concerns, imagine yourself as a molecular archaeologist reading the crystalline libraries that volcanic processes have written in stone across billions of years. Each mineral crystal is a book, each chemical element a letter, each isotopic ratio a sentence in the grand narrative of planetary evolution. Zircon crystals represent perhaps the most remarkable of these geological libraries, preserving information about conditions on early Earth with fidelity that exceeds human historical records. These tiny grains, often smaller than the width of a human hair, incorporate uranium into their crystal structure with such precision that they serve as atomic chronometers, accurate to within millions of years over timescales of billions of years. The decay of uranium to lead occurs at rates so constant that they provide absolute time markers immune to weathering, metamorphism, or any other geological process. The hafnium isotope signatures preserved in zircon crystals tell even more remarkable stories about the chemical evolution of Earth's crust. Hafnium-176 is produced by the radioactive decay of lutetium-176 over geological time, creating isotope ratios that reflect the age and composition of the crustal rocks from which volcanic magmas were derived. These signatures reveal that some volcanic rocks contain recycled material from crustal rocks more than 3 billion years old, fragments of Earth's earliest continents incorporated into modern volcanic systems. Trace element patterns in volcanic minerals follow crystal chemical rules so precise they can be predicted from first principles of atomic physics. The substitution of rare earth elements into crystal structures depends on ionic radius and charge in ways that create diagnostic fingerprints for different geological processes. These patterns distinguish between magmas derived from oceanic versus continental sources, from shallow versus deep melting, and from oxidizing versus reducing conditions with remarkable sensitivity. The oxygen isotope ratios preserved in volcanic minerals provide pale othermometers that record the temperature conditions of magma crystallization with precision approaching 1 degree Celsius. These isotopic temperatures complement other geothermometers based on trace element partitioning and mineral equilibria, creating multiple independent constraints on the thermal history of volcanic systems. The consistency between different temperature estimates provides confidence in our understanding of ancient thermal processes. Melt inclusions, tiny droplets of magma trapped within crystals as they grow, represent direct samples of magmatic processes, frozen at specific moments in volcanic history. These microscopic time capsules preserve evidence of magma compositions, volatile contents, and storage conditions that would otherwise be lost during eruption and crystallization. Modern analytical techniques can extract chemical information from melt inclusions smaller than the period at the end of this sentence. The magnetic properties of volcanic rocks preserve records of Earth's magnetic field behavior that extend the historical record back millions of years. Paleomagnetic directions recorded in volcanic flows document the wandering of magnetic poles, reversals of field polarity, and variations in field intensity that reveal the dynamics of Earth's core convection system. These magnetic archives show that Earth's magnetic field has varied dramatically over geological time, including periods when the field was much weaker than today. Volcanic glass preserves non-equilibrium, chemical states that provide insights into rapid cooling processes impossible to reproduce in laboratory experiments. The molecular structure of volcanic glasses reflects the kinetics of atomic rearrangement during quenching from temperatures exceeding 1000 degrees Celsius to surface temperatures within hours or days. These quenched structures preserve evidence of high-temperature chemical processes that would otherwise be overprinted during slow cooling. The noble gas signatures trapped in volcanic minerals provide the most direct chemical links between volcanic processes and planetary formation. Helium isotope ratios distinguish between mantle sources that have remained isolated since planetary accretion and those that have been modified by addition of recycled crustal materials. These chemical fingerprints allow scientists to map the chemical structure of Earth's interior and track the recycling of surface materials back into the deep mantle. Sulfur isotope signatures in volcanic rocks reflect the oxidation state of magma sources and the involvement of seawater or evaporite minerals in magma generation. These signatures can distinguish between magmas derived from primitive mantle sources and those that have interacted with crustal rocks or sedimentary materials during their ascent. The sulfur isotope systematics of volcanic rocks provide constraints on the evolution of atmospheric oxygen and the sulfur cycle over geological time. The crystal size distributions in volcanic rocks follow statistical patterns that reflect nucleation and growth processes during magma cooling. These distributions can be quantified using concepts from materials science and statistical mechanics, providing insights into cooling rates, undercooling, and crystal growth kinetics that complement other petrological tools. The mathematical analysis of crystal populations reveals details about magma chamber processes that are invisible to direct observation. Cathodoluminescence images of volcanic minerals reveal internal structures that record growth histories with seasonal precision in some cases. The luminescence patterns result from trace amounts of activator elements such as manganese and rare earth elements that substitute into crystal structures in response to changing chemical conditions. These growth patterns preserve records of magma chamber processes with temporal resolution that can approach annual cycles in some volcanic systems. The planetary thermostat in action. As consciousness gently settles into sleep's warm embrace, picture Earth as a living system with volcanic processes serving as its planetary thermostat, maintaining surface temperatures within the narrow range necessary for liquid oceans and complex life across billions of years of solar evolution and continental drift. The carbonate-silicate cycle represents one of nature's most elegant feedback systems, coupling volcanic outgassing with chemical weathering in a planetary-scale negative feedback loop. As volcanic emissions increase atmospheric carbon dioxide, global temperatures rise, accelerating the chemical weathering of silicate rocks. This enhanced weathering removes CO2 from the atmosphere through the formation of carbonate minerals, providing a stabilizing influence on climate over geological timescales. The mathematical description of this thermostat involves coupled differential equations that relate temperature, atmospheric composition, weathering rates, and volcanic outgassing through parameters determined by solar luminosity, continental distribution, and ocean chemistry. These equations predict that Earth's surface temperature should remain within about 50 degrees of its current value despite variations in volcanic activity, solar brightness, and continental configuration, a prediction confirmed by geological evidence spanning billions of years. The role of plate tectonics in this thermostat system becomes apparent when we consider how continental distribution affects weathering rates and ocean circulation. When continents cluster in tropical latitudes, as they did during certain periods in Earth's history, enhanced chemical weathering draws down atmospheric CO2, leading to global cooling and ice age conditions. Conversely, when continents are concentrated at high latitudes, reduced weathering allows volcanic CO2 to accumulate, producing greenhouse conditions. The response time of this planetary thermostat varies from thousands to millions of years, depending on the magnitude of perturbations and the availability of weatherable silicate rocks. Small changes in volcanic outgassing can be buffered by adjustments in weathering rates within thousands of years, while larger perturbations may require continental-scale reorganization of weathering patterns over millions of years. This hierarchy of response times provides stability across multiple temporal scales. Ocean chemistry plays a crucial role in this thermostat through its control on carbonate precipitation and dissolution. The pH and alkalinity of seawater determine the saturation state with respect to carbonate minerals, affecting the efficiency of CO2 removal from the atmosphere. Volcanic emissions that change ocean chemistry can therefore alter the operation of the carbonate-silicate cycle, creating additional feedback loops that affect global climate stability. The weathering of volcanic rocks themselves contributes disproportionately to this planetary thermostat because of their high surface area and chemical reactivity. Fresh volcanic ash and lava flows weather much more rapidly than older crystalline rocks, creating a direct feedback between volcanic activity and atmospheric CO2 removal. This means that periods of intense volcanism trigger enhanced weathering that partially compensates for increased volcanic CO2 emissions. The biological enhancement of chemical weathering adds another layer of complexity to this thermostat system. Plant roots and microbial communities accelerate the dissolution of silicate minerals through the production of organic acids and the maintenance of chemically aggressive soil solutions. The evolution of land plants during the Devonian period may have fundamentally altered the operation of Earth's thermostat by dramatically increasing weathering rates. Ice ages represent periods when the planetary thermostat operates near its lower stability limit, with ice albedo feedbacks creating rapid transitions between glacial and interglacial states. The correlation between ice age timing and volcanic activity suggests that variations in outgassing rates can trigger transitions between different climate states when the thermostat system is operating near these critical thresholds. The atmospheric residence time of volcanic CO2 depends on the chemical composition of volcanic emissions and their interaction with existing atmospheric chemistry. CO2 from different volcanic sources may have different environmental impacts depending on the ratio of CO2 to sulfur compounds and other trace gases. This compositional complexity means that the climate effects of volcanism cannot be predicted solely from CO2 emission rates. Isotopic studies of ancient carbonates and organic matter reveal how the planetary thermostat has responded to major perturbations throughout Earth's history. The carbon isotope record shows clear signatures of periods when volcanic outgassing overwhelmed weathering capacity, leading to greenhouse conditions and mass extinction events. These episodes demonstrate both the power of volcanic forcing and the ultimate resilience of Earth's climate regulation systems. The discovery of similar carbonate-silicate cycles on other planets provides perspective on Earth's thermostat system. Mars appears to have lost its atmospheric CO2 through a combination of solar wind stripping and the cessation of volcanic outgassing when its interior cooled below the threshold for sustained volcanism. Venus may represent the opposite extreme, where runaway volcanic outgassing overwhelmed any weathering-based stabilization mechanism. Modern human activities are testing the capacity of Earth's thermostat system by adding CO2 to the atmosphere at rates that exceed volcanic outgassing by more than 2 orders of magnitude. The response of the weathering system to this perturbation will determine whether Earth's climate remains within its historical range of variability or transitions to a new stable state with fundamentally different characteristics. The mathematics of magma. In the drowsy mathematics of approaching dreams, let us explore how volcanic processes follow mathematical principles as elegant and universal as those governing planetary orbits or quantum mechanical systems. The behavior of magma, from its generation in the deep mantle to its final crystallization at the surface, can be described by equations that reveal the underlying order within apparent volcanic chaos. The partial differential equations governing heat conduction in Earth's interior determine where and when melting occurs in the mantle through a complex interplay of temperature, pressure, and composition. The geotherm, the temperature profile within Earth, intersects the solidus, the temperature at which rock begins to melt, only under specific conditions of pressure relief, volatile addition, or enhanced heating. These intersections define the three-dimensional geometry of melt generation zones beneath volcanic regions. Darcy's law, originally developed to describe groundwater flow, governs the movement of magma through the porous matrix of partially molten mantle rock. The permeability of this matrix depends on the fraction of melt present and its geometric distribution in ways that can be calculated from percolation theory and network topology. Below a critical melt fraction of about 0.07, magma remains isolated in disconnected pockets. Above this threshold, it can segregate and ascend toward the surface. The ascent of magma through the lithosphere follows principles of fluid dynamics modified by temperature-dependent viscosity, volatile exsolution, and crystallization. The Reynolds number for magma flow is typically much less than unity, indicating laminar flow conditions, but the Peclet number can be quite large, indicating that heat transfer is dominated by advection rather than conduction. These dimensionless parameters determine whether ascending magma will remain molten or crystallized during transport. The shape of volcanic edifices reflects the balance between eruption rate, magma properties, and erosional processes through relationships that can be expressed in terms of dimensional analysis and scaling laws. The height-to-width ratio of stratovolcanoes correlates with the viscosity and gas content of their erupted magmas, according to theoretical models based on fluid mechanics and materials science. These scaling relationships allow volcanologists to infer magma properties from volcanic landforms. Crystal nucleation and growth in magmas follow kinetic equations derived from classical nucleation theory and interface-controlled growth models. The number density of crystals and their size distributions can be predicted from undercooling, interfacial energy, and diffusion rates using mathematical frameworks developed for industrial crystallization processes. These models successfully explain the textural diversity of volcanic rocks and provide quantitative tools for interpreting cooling histories. The exsolution of volatile components from magma as it ascends and decompresses follows Henry's law and other thermodynamic relationships, but with complications arising from the non-ideal behavior of magmatic solutions at high temperatures and pressures. The solubility of water in silicate melts, for example, depends on pressure according to a square root relationship that determines the depth at which volatile saturation occurs and explosive eruptions become possible. Volcanic eruption dynamics can be modeled using computational fluid dynamics codes that solve the Navier-Stokes equations for two-phase flow of gas and magma. These models predict eruption column heights, mass discharge rates, and pyroclast dispersal patterns from initial conditions specified by magma chamber properties and vent geometry. The agreement between model predictions and observed eruption phenomena validates our understanding of the physics governing explosive volcanism. The propagation of volcanic tsunamis follows the shallow water wave equations, with source terms determined by the volume and velocity of volcanic mass flows entering the ocean. The mathematical analysis of these waves reveals that their amplitudes and travel times depend on water depth, source geometry, and bathymetry in predictable ways. These models are essential for tsunami hazard assessment in volcanic regions. Seismic wave propagation through volcanic regions provides constraints on subsurface structure through travel time analysis and waveform modeling. P-wave and S-wave velocities vary systematically with temperature, melt fraction, and rock composition, according to empirical relationships derived from laboratory measurements and theoretical calculations. These seismic models reveal the three-dimensional architecture of magma storage systems, with resolution approaching hundreds of meters in well-monitored volcanic regions. The fractal geometry of volcanic systems reflects self-similar scaling relationships that appear at multiple spatial and temporal scales. The size-frequency distribution of volcanic eruptions follows power law relationships similar to those observed for earthquakes, landslides, and other natural phenomena, governed by critical point dynamics. These scale-invariant patterns suggest that volcanic systems operate near critical thresholds where small perturbations can trigger large-scale reorganization events. Chaos theory applications to volcanic systems reveal how deterministic processes can produce apparently random behavior through sensitive dependence on initial conditions. The timing of volcanic eruptions may be fundamentally unpredictable beyond certain time horizons, even with perfect knowledge of system state, due to the non-linear coupling between multiple feedback processes. This mathematical framework helps explain why volcanic forecasting remains challenging despite advances in monitoring technology. The whispering stones of ancient atmospheres. As sleep's gentle current carries you deeper into geological dreamtime, imagine yourself as an atmospheric chemist reading the whispered secrets that volcanic rocks have preserved about Earth's ancient skies. Each crystal, each glass fragment, each tiny bubble trapped in lava contains chemical messages about atmospheres that existed millions or billions of years before the first human breath. The volcanic glasses formed during submarine eruptions represent some of our most pristine samples of ancient atmospheric chemistry. When magma erupts underwater, it cools so rapidly that volatile components are trapped within the glass structure before they can escape to the overlying water column. These quenched volatiles preserve the exact chemical composition of volcanic gases at the moment of eruption, including species that would otherwise react and disappear within hours or days. Mass spectrometric analysis of these volcanic glasses reveals atmospheric oxygen levels throughout Earth's history, with precision that complements other paleochemical proxies. The oxidation state of iron in volcanic glasses reflects the fugacity of oxygen in the atmosphere at the time of eruption through equilibrium relationships that can be calibrated using experimental petrology. These measurements show that atmospheric oxygen rose from essentially zero levels in the Archean to nearly modern values during the Proterozoic, with fluctuations that correlate with major evolutionary transitions. The noble gas signatures trapped in volcanic minerals provide even more direct information about ancient atmospheric composition and evolution. Xenon isotope ratios in volcanic glasses preserve evidence of early atmospheric loss processes, including hydrodynamic escape driven by intense solar ultraviolet radiation and impacts from large asteroids or comets. These isotopic signatures reveal that Earth's early atmosphere was much denser than today and contained significant amounts of hydrogen and helium inherited from the solar nebula. Sulfur isotope patterns in ancient volcanic rocks record the evolution of atmospheric photochemistry over billions of years. The appearance of mass-independent sulfur isotope fractionation in rocks older than 2.4 billion years indicates that atmospheric oxygen levels were below about 1 part per million, too low to form an ozone layer that would shield sulfur compounds from ultraviolet photolysis. The disappearance of these anomalous isotope signatures marks the Great Oxidation Event, when rising oxygen levels fundamentally altered Earth's atmospheric chemistry. Carbon isotope signatures in volcanic carbonates and organic matter reveal the evolution of the carbon cycle and its coupling to atmospheric composition over geological time. The ratio of carbon-12 to carbon-13 in ancient volcanic rocks reflects the balance between organic carbon burial and carbonate precipitation, processes that control atmospheric CO2 levels over millions of years. These isotopic records show that atmospheric CO2 concentrations have varied by more than an order of magnitude throughout Earth's history. Nitrogen isotope ratios in volcanic rocks provide constraints on atmospheric pressure and composition that complement other paleochemical indicators. The isotopic composition of atmospheric nitrogen has remained remarkably constant over geological time, but its preservation in volcanic minerals depends on pressure and temperature conditions that can be used to infer atmospheric density. These measurements suggest that atmospheric pressure may have been significantly higher during certain periods in Earth's history. The trace element chemistry of volcanic glasses preserves information about atmospheric dust loading and composition that reflects both volcanic activity and extraterrestrial input. Iridium and other platinum group elements in volcanic glasses show baseline concentrations interrupted by spikes corresponding to large asteroid impacts. These chemical signatures provide independent confirmation of impact events identified through other geological evidence. Volcanic aerosol particles preserved in ice cores extend the atmospheric record back hundreds of thousands of years, with annual resolution in some cases. The chemical composition and size distribution of these particles reflect not only the intensity of past volcanic eruptions, but also their impact on atmospheric chemistry and climate. The sulfur isotope ratios of volcanic aerosols preserved in ice can be used to identify specific volcanic sources and track atmospheric transport patterns. The interaction between volcanic gases and atmospheric water vapor creates secondary minerals that preserve detailed records of ancient humidity and temperature conditions. Zeolite minerals formed by the reaction of volcanic ash with atmospheric moisture retain molecular water with hydrogen and oxygen isotope ratios that reflect the temperature and humidity of ancient atmospheres. These hydrated volcanic glasses serve as paleohygrometers with precision approaching modern meteorological instruments. Volcanic lightning generates nitrogen compounds that become incorporated into volcanic ash and ultimately preserved in sedimentary records. The abundance of these lightning-produced nitrates in ancient volcanic deposits provides estimates of lightning frequency and atmospheric electrical activity during past eruptions. This information complements other paleoclimatic indicators and helps reconstruct ancient storm patterns and atmospheric dynamics. The preservation of volcanic gases in fluid inclusions within crystals provides direct samples of ancient volcanic emissions that can be analyzed using modern analytical techniques. These microscopic gas bubbles contain mixtures of CO2, H2O, SO2, and other species with compositions that reflect both magmatic processes and atmospheric interaction. The noble gas ratios in these inclusions distinguish between mantle-derived and atmosphere-derived components with remarkable sensitivity. The symphonic convergence of fire and life. In the deepening tranquility of sleep's approach, Let your consciousness drift toward the profound realization that life and volcanism have danced together for billions of years in an intricate choreography of mutual dependence and evolutionary innovation. This is not merely coexistence, but a fundamental partnership that has shaped the chemistry of our planet and the trajectory of biological evolution in ways both subtle and dramatic. The origin of life on Earth may itself be intimately connected to volcanic processes through the creation of chemical gradients and energy sources necessary for the first self-replicating systems. Hydrothermal vents associated with submarine volcanism create natural laboratories where organic synthesis occurs under conditions that may have prevailed on early Earth. The mineral surfaces provided by volcanic rocks serve as catalysts for organic reactions, concentrating reactants, and facilitating the formation of complex molecules from simple precursors. The iron-sulfur world hypothesis proposes that volcanic hydrothermal systems provided the chemical foundation for early metabolism through reactions between volcanic gases and metal sulfide minerals. These reactions can drive the reduction of carbon dioxide to organic compounds using chemical energy derived from volcanic heat, creating a pathway from geochemistry to biochemistry that requires no external energy source. Modern archaea that thrive in volcanic hot springs may represent evolutionary descendants of these earliest metabolic systems. Volcanic ash contributes essential nutrients to terrestrial and marine ecosystems through the weathering and dissolution of volcanic glass and minerals. The trace elements released during ash weathering, iron, manganese, zinc, cobalt, and others, often limit biological productivity in regions far from volcanic sources. Major explosive eruptions can fertilize entire ocean basins with these micronutrients, triggering algal blooms that affect marine food webs and atmospheric CO2 levels. The timing of major evolutionary innovations often correlates with periods of intense volcanic activity, suggesting that environmental stress associated with volcanism may accelerate evolutionary change through selection pressure and genetic innovation. The Cambrian explosion, the evolution of land plants, and the diversification of mammals all occurred during or shortly after periods of significant volcanic upheaval. This correlation may reflect the role of environmental change in opening new ecological niches and driving adaptive radiation. Extremophile organisms that thrive in volcanic environments represent some of the most ancient lineages on Earth and provide insights into the limits of life under extreme conditions. Hyperthermophile archaea, living in volcanic hot springs at temperatures exceeding 100 degrees Celsius, use metabolic pathways that may preserve biochemical strategies from early Earth, when surface temperatures were much higher. These organisms demonstrate that life can adapt to conditions that would destroy most modern species. The symbiotic relationships between volcanic activity and photosynthetic organisms reveal complex feedback loops between geological and biological processes. Volcanic SO2 emissions provide the raw material for photosynthesis, while biological productivity affects atmospheric oxygen levels and weathering rates that influence volcanic chemistry. Large igneous province eruptions can disrupt this balance, leading to mass extinctions followed by evolutionary recovery and diversification. Volcanic soils support some of the most biodiverse terrestrial ecosystems on Earth through their unique chemical and physical properties. The high porosity and water retention capacity of volcanic ash create favorable conditions for plant root development, while the slow release of nutrients during mineral weathering provides sustained fertility. Endemic plant species have evolved in volcanic regions worldwide, adapted to specific chemical conditions created by local volcanic rocks. The role of volcanic gases in atmospheric evolution demonstrates how geological processes have maintained conditions suitable for complex life over billions of years. Volcanic outgassing of water vapor, carbon dioxide, and nitrogen created Earth's secondary atmosphere after the loss of the original hydrogen-helium atmosphere inherited from the solar nebula. The continued release of these gases balances their removal by biological and chemical processes, maintaining atmospheric composition within narrow limits. Marine organisms construct shells and skeletons from carbonate minerals whose chemistry reflects both biological processes and volcanic influence on ocean chemistry. The isotopic composition of marine carbonates preserves records of ancient ocean temperatures, atmospheric CO2 levels, and volcanic activity extending back hundreds of millions of years. These biological archives provide high-resolution records of Earth system evolution that complement direct geological evidence. Volcanic winter effects following large eruptions create natural experiments in ecosystem response to rapid environmental change. The cooling and altered precipitation patterns following major eruptions provide analogues for other types of rapid climate change, revealing both the vulnerability and resilience of biological systems. Recovery patterns following volcanic disturbances illuminate the mechanisms by which ecosystems reorganize after major perturbations. The chemical evolution of seawater reflects the long-term balance between volcanic input and biological removal of dissolved species. Marine organisms extract calcium, silicon, and carbon from seawater to construct shells and skeletons, while volcanic input provides these elements through weathering and direct hydrothermal discharge. This biogeochemical cycling has maintained ocean chemistry within narrow limits, suitable for calcifying organisms over hundreds of millions of years. Pollination relationships between plants and animals have been influenced by volcanic activity through its effects on vegetation patterns and climate. Volcanic barriers can isolate populations and drive speciation, while volcanic soils support plant communities with distinctive flowering times and nectar chemistry. The coevolution of flowering plants and their pollinators has been shaped by the fragmented landscapes created by volcanic activity. The cosmic context of terrestrial fire. As your breathing deepens in rhythm with the approaching tide of sleep, let your imagination expand beyond Earth to contemplate how our planet's volcanic activity fits within the broader cosmic story of planetary evolution and the search for life in the universe. The fire that burns beneath our feet is part of a universal process that shapes worlds across the galaxy and perhaps determines their habitability. Comparative planetology reveals that volcanism is a fundamental process in the evolution of rocky planets, but its expression depends critically on planetary mass, composition, and orbital characteristics. Mars, with roughly half Earth's diameter and 1/10 its mass, lost its internal heat more rapidly than Earth, leading to the cessation of global volcanic activity within its first 2 billion years. The giant shield volcanoes of Mars, including Olympus Mons, grew to enormous sizes because the absence of plate tectonics allowed volcanic activity to remain focused at fixed locations for millions of years. Venus presents a dramatically different volcanic story, with surface conditions so extreme that direct observation of active volcanism remains impossible. Radar mapping through the planet's dense atmosphere reveals volcanic features covering more than 80% of the surface, including vast plains of flood basalts, shield volcanoes larger than any on Earth, and unique volcanic landforms called coronae that have no terrestrial analogues. The extreme greenhouse effect on Venus may be partly maintained by continued volcanic outgassing of CO2 and sulfur compounds. The icy satellites of the outer solar system demonstrate that volcanism can occur even in environments where water ice takes the place of silicate rock. Enceladus, Saturn's sixth largest moon, erupts plumes of water vapor and ice particles from fractures near its south pole, powered by tidal heating as it orbits within Saturn's gravitational field. These cryovolcanic eruptions may sustain a subsurface ocean that represents one of the most promising environments for extraterrestrial life in our solar system. Io, Jupiter's innermost large moon, experiences the most intense volcanism in the solar system due to gravitational flexing caused by its orbital resonance with Europa and Ganymede. This tidal heating maintains hundreds of active volcanoes that continuously resurface the moon with sulfur compounds, creating a landscape painted in brilliant yellows, oranges, and reds. The volcanic activity on Io demonstrates how gravitational forces can maintain geological activity for billions of years even in the absence of radioactive heating. The detection of volcanic activity on exoplanets represents one of the most exciting frontiers in planetary science and astrobiology. Theoretical models predict that many rocky exoplanets should experience volcanism, particularly those in close orbits around their host stars, where tidal heating can supplement radioactive heat sources. Future space telescopes may be able to detect volcanic outgassing in exoplanet atmospheres, providing insights into their geological activity and potential habitability. The relationship between volcanism and habitability extends beyond the simple provision of atmospheres and oceans to include more subtle effects on climate stability and geochemical cycling. Planets with active volcanism can maintain long-term climate stability through the carbonate-silicate cycle, while geologically dead worlds like Mars may lose their atmospheres to space over geological time. The presence of volcanism may therefore be a requirement for the long-term habitability of rocky planets. Asteroid and comet impacts can trigger volcanic activity through the sudden injection of heat and volatiles into planetary crusts. The Chicxulub impact that contributed to the extinction of non-avian dinosaurs may have enhanced volcanic activity at the Deccan Traps in India, demonstrating how external perturbations can influence planetary volcanic systems. Similar impact volcanism coupling may occur on other worlds and could be detectable through spectroscopic observations of exoplanet atmospheres. The chemical evolution of stellar systems affects the composition of planetary building materials, and therefore the style of volcanism that develops on rocky planets. Stars with different metallicities, abundances of elements heavier than helium, produce rocky planets with different compositions that affect their melting behavior, volatile content, and volcanic activity. First-generation stars in the early universe produced planets with very different volcanic characteristics than those forming around younger metal-rich stars today. The search for biosignatures in exoplanet atmospheres must account for volcanic processes that can mimic biological activity or obscure genuine biological signals. Volcanic outgassing can produce oxygen, methane, and other gases that might otherwise be interpreted as evidence of life. Understanding volcanic processes on Earth and other solar system bodies provides the foundation for distinguishing between biological and geological sources of atmospheric gases on distant worlds. Galactic cosmic rays and stellar radiation can influence volcanic activity on exoplanets through their effects on atmospheric chemistry and upper mantle convection. High-energy particles can drive atmospheric loss and alter the oxidation state of planetary surfaces and interiors. Planets orbiting different types of stars may experience different levels of radiation that affect their volcanic evolution and long-term habitability. The timing of volcanic activity relative to the late heavy bombardment and other early solar system processes may have been crucial for the development of life on Earth. Volcanic outgassing during and after the period of intense asteroid and comet impacts helped rebuild Earth's atmosphere and oceans, creating conditions suitable for the origin of life. Similar sequences of events may be necessary for habitability on exoplanets around other stars. Binary and multiple star systems present unique challenges and opportunities for volcanic evolution on planetary bodies. Gravitational perturbations from stellar companions can drive orbital eccentricity variations that enhance tidal heating and volcanic activity. Some of the most volcanically active worlds in the galaxy may orbit within multiple star systems where complex gravitational interactions maintain geological activity over billions of years. The eternal dance of creation and renewal. In the final, drowsy moments before sleep, claims your consciousness, rest in the profound understanding that volcanic fire represents one of the universe's most fundamental creative forces, not just on Earth, but wherever rocky worlds gather, the cosmic dust of stellar nucleosynthesis, and forge it into the complex chemistry necessary for oceans, atmospheres, and ultimately life itself. The volcanic processes we observe today are direct descendants of the nuclear fusion reactions occurring in stellar cores, where hydrogen atoms are welded together to form helium, releasing the energy that powers stars and creates the heavier elements that become the raw materials of rocky planets. The iron in volcanic basalts, the silicon in volcanic glasses, and the sulfur in volcanic gases were all forged in stellar furnaces and scattered through space by supernova explosions billions of years ago. This cosmic connection extends beyond simple elemental composition to include the isotopic signatures that preserve evidence of stellar nucleosynthesis processes. The ratios of different isotopes of elements like oxygen, silicon, and iron in volcanic rocks reflect the specific nuclear reactions that created them in different types of stars. By studying these isotopic patterns, volcanologists become cosmic archaeologists, reading the history of stellar evolution written in terrestrial stones. The energy that drives volcanic activity today comes from multiple sources that connect Earth's interior to cosmic processes operating on vastly different timescales. Radioactive decay of uranium, thorium, and potassium provides steady heat production that has powered plate tectonics and volcanism for billions of years. The gravitational potential energy released during Earth's accretion from the solar nebula remains stored in our planet's interior, slowly leaking to the surface through volcanic processes. Tidal heating from gravitational interactions adds another cosmic component to volcanic energy budgets, particularly for satellites orbiting gas giant planets. The same gravitational forces that create ocean tides on Earth produce internal heating in moons like Io and Enceladus, demonstrating how orbital mechanics can maintain geological activity long after radioactive heating has declined. These tidal effects operate according to celestial mechanical principles that connect volcanic activity to the architecture of planetary systems. The distribution of volcanic activity across the solar system reflects fundamental principles of planetary science that may apply to exoplanetary systems around other stars. Smaller bodies lose their internal heat more rapidly than larger ones, leading to shorter periods of volcanic activity. Bodies with eccentric orbits or complex orbital resonances may experience enhanced tidal heating that extends their geological lifetimes. These scaling relationships provide frameworks for predicting volcanic activity on newly discovered exoplanets. The atmospheric consequences of volcanism demonstrate how local geological processes can have global and even interplanetary effects. Large volcanic eruptions on Earth inject aerosols into the stratosphere that affect global climate for years. Similar processes on Mars may have contributed to climate change that transformed it from a warmer, wetter world to its current cold, arid state. Volcanic outgassing on Venus may have triggered the runaway greenhouse effect that created its hellish surface conditions. The geochemical cycles mediated by volcanism connect Earth's interior to its surface environment through pathways that operate over time scales ranging from days to billions of years. The carbon cycle, nitrogen cycle, and sulfur cycle all depend on volcanic processes to maintain the atmospheric composition necessary for life. These biogeochemical connections may represent universal requirements for habitability on rocky planets throughout the galaxy. The role of volcanism in planetary magnetic field generation adds another layer to its cosmic significance. The convection of molten iron in planetary cores, driven partly by thermal and chemical gradients maintained by volcanic processes, generates magnetic fields that shield planetary surfaces from harmful cosmic radiation. The loss of volcanic activity on Mars coincided with the decay of its magnetic field, suggesting that continued geological activity may be necessary for maintaining habitable conditions on rocky planets. The preservation of volcanic processes in the geological record provides Earth with a memory that extends back billions of years, recording not only terrestrial events, but also cosmic influences on planetary evolution. Impact events recorded in volcanic rocks document the history of asteroid and comet bombardment. Volcanic sediments preserve evidence of nearby supernova explosions and other cosmic events that have influenced Earth's environment over geological time. The study of volcanic processes on Earth provides the foundation for understanding similar phenomena throughout the universe. The physical and chemical principles governing magma generation, transport, and eruption operate universally, constrained by the same fundamental constants and natural laws that apply everywhere in the cosmos. Earth's volcanoes serve as natural laboratories for processes that may be occurring on countless worlds orbiting distant stars. The future evolution of Earth's volcanic systems will be determined by the same cosmic processes that have shaped planetary evolution throughout the universe. As our sun gradually brightens over the next billion years, Earth's climate system will be challenged to maintain habitable conditions. Volcanic processes, through their role in the carbonate-silicate cycle, will play a crucial role in determining whether Earth can adapt to these changing stellar conditions. The search for life elsewhere in the universe must therefore include consideration of volcanic processes as both indicators of habitability and potential sources of biosignatures. Active volcanism may be necessary to maintain the atmospheric and oceanic conditions required for complex life over geological timescales. The detection of volcanic activity on exoplanets through atmospheric spectroscopy or thermal emission may therefore represent an important step in identifying potentially habitable worlds. As you drift into sleep, carry with you the knowledge that the volcanic fire beneath our feet connects us to the deepest processes of cosmic evolution. Every breath you take contains atoms forged in stellar cores and delivered to Earth's surface through billions of years of volcanic outgassing. Every landscape you see has been shaped by the patient work of volcanic processes operating according to physical laws that govern the evolution of worlds throughout the universe. In the gentle darkness of approaching dreams, the volcanoes of Earth continue their ancient work, breathing out the chemical essence of stars and slowly building the foundations for future chapters in the cosmic story of matter, energy, and the eternal dance between creation and renewal. Rest well in the knowledge that you are part of this vast, interconnected system, a temporary arrangement of cosmic dust made conscious through the patient creativity of volcanic fire working across deep time. The ring of fire burns on, not as a threat or curiosity, but as a reminder of our cosmic heritage and a promise that the universe continues its work of transformation, always creating new possibilities from the endless recycling of stellar matter. In Volcanoes' fire, we see both our origins and our destiny, children of stars, shaped by planetary forces, participants in the universe's ongoing experiment with complexity, consciousness, and the delicate beauty of worlds that dare to dream.